Okay, welcome to UCLA QC Bio Collaborative Workshop 1B for, what is this? This is spring 2024, UNIX Command Line II. So historically, we had Workshop 1 was our intro to Unix workshop for a long time. And then a couple years ago, we added Workshop 36, which is sort of an advanced form of it. But students have for a long time kind of given us the feedback that they found Workshop 1 kind of too packed. And it's just too much to take in kind of all at once. And so this is the first quarter we're going to try splitting what formerly was Workshop 1 into two parts. So Workshop A and B. Did you guys take Workshop A just like a couple of weeks ago? Or yeah, at least some of you. Right. So I'm going to assume it's okay if you haven't, but I'm going to assume that you've like logged into Hoffman before and like you know something, right? I don't want to start from zero. But the goal here is to sort of, I mean, we'll kind of be reviewing that material, of course, but we're going to extend it and kind of fill in some gaps, add more details, kind of move you closer to kind of doing real work. Whereas kind of like in Workshop 1, just to learn the commands at all, it's sort of like you're overwhelmed with that, and it's like hard to really apply those to like real situations, right? You just kind of just learning it from the beginning. So yeah, we'll try to kind of have some more motivated examples in this one. And you know, there's more the core Unix utilities will show, and we'll show the ones that you've already seen used in some new ways. And then we're going to put those tools together into bigger things now. So you probably saw at least like some pipeline stuff with the pipe symbol and the redirection less than and greater than sign, but we're going to really get into that in here and like actually use that to kind of build up more interesting things with that. And then we'll get into some of the fancier shell features that are very important for doing repetitive tasks, which is like what you normally find yourself in research work, right? You've got to do something to all your samples or whatever. You've got some analysis pipeline that's got many steps and you got to pump a lot of data through it. And there's shell features that help a lot with that. And then other features that help out with that are like loops, functions, and scripts. And we'll talk a little bit about those. But these are all big topics that we can't like completely cover. Even in Workshop B, that's why there's things like Workshop 36, and you just kind of learn these things over time as you kind of really get into situations that require them. But we'll start you on the way here. And the other thing we're doing in Workshop 1B is to set up for Workshop 36, which is the conclusion of the series. And that basically uses a case study of a real bioinformatics problem to kind of get you to the point where you can run fairly large scale stuff on Hoffman, things with thousands or tens of thousands of parts. Today, we'll get in this Workshop 1B, we'll get to the point where you can run small and medium sized problems on Hoffman, things with maybe up to dozens or hundreds of parts. And Workshop 36 ends with sort of a bunch of templates for you to use to sort of that make it easy to kind of like bring new problems into this flexible, scalable way that Workshop 36 covers. So anyway, but this is all kind of new. So we're kind of like this division of what's in Workshop 1A, 1B, and 36 is all kind of shifting right now. And since I haven't taught this one before, I'm not quite sure how fast we're going to go and we're going to end up, but it'll all be okay. But this is all sort of in flux while we sort of figure out what this new division is between things. So I'm going to start with just some quick review and whatever, and maybe some details. So you know, the command line, maybe you guys all started your life probably on GUIs, right? You know, long it's been out for a long time. So you probably think of this sort of command line stuff, kind of this ancient weird stuff from the dawn of computing. Why is it still around? Well, there's a bunch of reasons, and you know, you can read this slide on your own time or whatever. Maybe you already appreciate some of these, but basically, for a lot of things, there's no better way to do it. Nobody's really found it. It's just so efficient in terms of the way you use the computer and your own time once you get facility with it. And no one's really found anything better. And so a huge amount of you know, computational work around the world is all done in this way. And a lot of tools are only available in this way and so on. And especially when you want to automate things repetitively or do things repetitively or automate things, or put software together into bigger pieces, you can't really do it by clicking and stuff. You got to kind of get into this world. And that's why it persists. So Unix, created by Kernighan and Ritchie, I think that PDP 11 in the 70s, there they are down there. 50 years later, still going strong. In fact, iPhones, probably the biggest deployed base of Unix computers in the world right now. BSD Unix, well, it's Mac OS, it's all the same on all their platform, basically, iOS and so on. It's based on BSD Unix, which is a derivative of Unix. And even though they don't expose that on the phone, if you're a developer or if you jailbreak and stuff, that's what this phone's running. So yeah, it's just been incredibly successful. You know, Research Unix was born here in the 70s. It kind of spread out to a lot of branches. And this is a much more, you know, you can kind of just see, like, sort of at the early stage, it kind of branched hugely. It's thinned out a bit now. Now there's basically the BSDs left, which are mostly kind of, you don't, behind the scenes and sort of like server farms and stuff. The Apple universe, very prominent. Linux, of course, huge. And that's what Hoffman runs. And then there's sort of like Oracle has their own Solaris stuff and whatever. That's even kind of probably on the decline. It's basically the BSDs, the Apple and Linux, which is probably the reverse order. I should have said that. Then Linux is the biggest. So when we use Hoffman on our personal laptops and stuff, this is it's really the same thing as just we were back in the 80s, really. You know, and the original thing, it was actually on paper, teletypes. Then there were glass terminals. You didn't have to waste so much paper. Basically, that's what your laptop does when you connect to Hoffman with SSH. You're simulating those old glass TTYs of the 80s. This is a little picture of a fraction of Hoffman. I think it occupies multiple rooms over that way somewhere. And yeah, Linux is 100% of the top 500 supercomputers in the world right now. Hoffman 2 is the biggest campus cluster on the UCs. It runs CentOS 7.9 2009 right now. The job queue system, which we'll get to at the end on day 3, is UGE, Univa Grid Engine. That used to be called SGE, but whatever. That's a very common one you find on large clusters. And just to give you some rough statistics so you kind of know how big it is, there's about 16 to 192 CPUs per node. A node is like one little physical box, like one computer, say. And there's about 24,000 cores total in the system. And the amount of memory per node, one computer, is about 120 gigabytes to 6 terabytes of RAM per node. And the total across the whole cluster is about 140 terabytes. If you divide it out, on average, it turns out to be that it's something like 5 gigabytes on average RAM per core. So for example, when we use the queue system and we have to ask for resources, so it's going to depend upon what you're doing, but just, if you kind of just want a default, you just think about 5. How many cores do you want to use times by 5? That's about how much RAM is about right to ask for, because that's what the cluster can sort of sustain on that. Let's see if this cable, which has always been flaky in this room, comes back. There we go. And did the screen sharing on Zoom still keep going? Maybe I should stop sharing, reshare, make sure it's still going. Okay. All right. There's petabytes of hard storage on that on the cluster. Of course, the problem is you get a very little amount just by being a regular campus member. If you're part of a group, like your research group or your PI or something, put money in, you'll have more space, but that's like paid storage. And it's often full. And then there's also a scratch space, which is a free-for-all, but is generally much bigger. It's just that things aren't backed up and can be deleted at any time. We'll talk about that again in a second. And there's thousands of users on the system, not generally all logged in simultaneously, but there's thousands of accounts on that system. And at any one moment, there tends to be thousands of jobs running at that moment. Like once we play with Hoffman, we'll check it out at that time. All right, so hopefully you know a little bit about kind of the structure of Hoffman. We're out here on the outside. Basically, we're going to connect in from the general internet, the campus internet. And you're only supposed to connect to, these are the only machines that are exposed in yellow to the outside world. The ones that we care about are the login machines, called login nodes. There's only 4 of them, 1, 2, 3, 4. If you use the name login, you get one randomly, whatever, a round robin or whatever the heck they do inside, you don't have to care. But login.hoffman2.iter.ucla.edu just picks one. There's also NX and X2Go GUI ways to access Hoffman 2, which we're not going to talk about. And there's these DTN data transfer nodes, which are used for large moving data in and out of it, which maybe we'll talk a little bit about, but mostly you can notice too. But mostly these login guys, this is our point of entry. Then there's internal networking over there. And then there's all the racks of nodes. There's about 800 nodes in whatever, you can pack 10, 20 nodes in a rack or whatever. So it's quite a few racks. They have names like N1018, N7684, and so on, which we don't have to care about because the queue system will pick out which ones are available for us at any given moment. It's got some big schedule where it's trying to get everybody's jobs matched up with resources and so on and so on. There's a few GPU nodes, but there's not that many of them, and we won't care about those. The way you move from the login nodes to the work nodes is with the QSub and QRSH. Maybe you saw QRSH in Workshop 1A. And then these guys have talked as the storage servers. These are things like NetApp, high-speed flash file systems and stuff, petabytes of storage back here. Okay, so if this is a slide just full of links in case your Hawken stuff is screwed up, but there's the link to sign up. If you've got questions, there's the support ticket link. If you forgot your password, there's that link. There's also the documentation that the group that runs Hawken writes themselves. That's linked out here. And like I say, there's other ways of using Hawken besides text mode SSH, and there's a link there where the documentation from the cluster group documents that. So that's just full of some links for your reference. So other than that, let's get login to Hawken. Now, Workshop 1A should have gotten you that squared away, and it just depends on what software you want to use. So if you're on Mac or Linux, it's going to be probably Open SSH, Command Line SSH. That's going to be part of the OS base install, nothing to install. If you're on Windows, you're going to need some third-party software of some kind, most likely. So for me, all I got to do is SSH my username, my Hawken username, at the login dot you don't really need because that's actually, if you just leave that off, they also made that a synonym. So if you just do Hawken2 Israel UCLA edu, you're going to get one of the login nodes, right? There we go. And here I've actually set up passwordless SSH. So that's nice. I didn't have to type a password. Maybe Workshop 1A talked about that, maybe not. If you're interested in that, we can talk about that offline, like at the end of, after today's done. But this is a nice way to use it because this way you don't have to keep typing your password, and you can also script this stuff. So like, it's nicer to do it with this passwordless way. I didn't get any crypto warnings and stuff because my machine's already contacted Hawken before and knows the signature of Hawken and can verify that I'm still talking to the same machine I always have been, and so on. So yeah, so if you're on Mac, it looks something like this. If you're on Linux, it looks exactly the same. It's just that how you start your terminal emulator. For me, it's in my applications folder, utilities in here somewhere. And then this terminal.app is Apple's built-in part of the Mac OS terminal emulator. On Linux, you'll have some terminal emulator. It depends on which distribution you have and what your desktop is, KDE or GNOME and so on. But you'll have some terminal emulator. Once you start it, you do exactly the same things we did here. If you're on Windows, you got to do something right because you probably don't have software. Depending on how many optional components of Windows you have installed, you might actually have OpenSSH, the same program we're using here, this SSH program. You might have it at this place in your Windows directory already. You can actually use it that way if it's there. It's like an optional component of Windows that doesn't always get installed. Otherwise, you got to use something else like MOBA, Xterm, PuTTY, whatever. Then you got to configure your software with the right settings. And then at some point, you'll end up with a screen that looks just like we've got here. Or you could install Cygwin on Windows. That actually takes this whole set of Unix utilities, like the bash shell, head, tail, all the rest, recompiles them for Windows, and then kind of gives you a little nice installer where you can pick pieces of that. And so with that, you can actually open like a real bash shell on your Windows. It's actually a Windows program, but it's the same code as bash really is. And then you can just OpenSSH, you can also install as part of Cygwin, and then you can do exactly the same thing there. But you're just sort of running it all as native Windows programs at that point. They've all been recompiled. Another option on Windows is to use the like a virtual machine. Like you could use VirtualBox or something, or Microsoft itself now has the Windows subsystem for Linux, WSL. And what that is it'll download a whole Linux distribution, open up a virtual machine, a simulated PC inside your PC, and you're actually running a real Linux kernel in there and the entire Ubuntu universe or whatever distribution you chose and so on. And at that point, you're really just talking to a Unix system inside. It's just being simulated inside your Windows machine. And then, of course, at that point, you can look exactly like the other ways too. So those are your options. Hopefully you've got something like working, like everybody, yes, you're logged in right now, you're okay. Okay, great. And this is a slide you can pretty much ignore, but if someday in a year or two you look back at this, maybe you'll be interested in the details, but it's basically all this machinery of the way the operating systems work today, the terminal emulator, the SSH program, the internet. And so we're basically just making a virtual serial cable that's miles long to get us over to the other building. But it's as if, it's just basically a way of virtualizing the old serial universe. It's still, from the point of view of the Unix programs inside and so on, just as if we were sitting there, hunched over in a warm room, typing with a physical cable connecting us to the machine. Okay, so of course, when we log in, the first thing that we're talking to is a Unix shell, right? So here, this is a prompt from the shell, and we're talking to the shell, and the shell's waiting for us to tell it to do something. So, just a reminder of what shells are and what they do. Shells are just programs. Unix machines are running lots of programs. Shells are one of the things they run. Happens to be the default program they start when you log in. Shells are programming languages. They are kind of designed for a very specific purpose and designed for interactive use, but shells provide a programming language. And so when we type into the shell, we're really composing little tiny programs. Oftentimes they're just one line at a time and whatever, and so on, and they tend to run immediately as we enter them. We don't like type huge programs of thousands of lines and run them all at once. But yeah, it's a programming language. And that means it has a syntax and a grammar and semantics, right? So there's ways that you build up what you type in and the way the shell takes them apart and interprets the pieces and then executes the pieces. The main purpose of shell, of course, is to start other programs. That's its main point in life. And so in some sense, the shell does nothing because it really just starts other things to do all the work. But in another sense, it does everything because that's how you get anything to happen at all. And Unix programs have a lot of state and surrounding context, things like the working directory and what files they're connected to when they start, and like security information and like computing limits and stuff like this. And a lot of the parts of the shell are designed to manipulate that environment, right? So the shell is starting all these programs for you, but it's got to build this whole, the whole environment and context for each program. And a lot of the shell stuff is about manipulating that context. So programs start with the context that you want them to have. Bash is the most common shell around. If you do PS $, you'll see what shell you're talking to. You see we're talking to a bash. That is probably the most common one on Linux. It used to be the default one on Mac too. Like if I open another terminal window before I even do SSH, I'm actually getting a shell to my local machine because my Mac is a Mac OS BSD-based Unix machine. And I'm getting a shell here, and if I ask here, I'm also typing to a bash. This is a local bash on my machine. Windows is a little different, of course, because unless you do the Cygwin or the WSL, you don't really have the bash shell on Windows. But yeah, so bash is the most common one. Mac has recently changed to Z shell, ZSH. But yeah, some people use Z shell, some use bash, K shell, C shell, T-sh, there's a ton of them. They've been around for more or less 50 years. There's a fairly well agreed upon big core that's all the same functionality and syntax and stuff. But once you get deep enough into a given shell, then there are differences. And then even bash has versions, so like the bash on Hoffman right now is 4.2.46. The bash on my Mac OS is 3.2.57. So this is like a bash 3, this is a bash 4. There will be some features this bash 4 has that my 3 doesn't, but not like features we're going to get into. That, kind of deeper features. But, it's not like there's broad compatibility, but it's not like they're all exactly the same. But let's put it that way. Then you did command line. You started composing command lines, basically little one-line programs that the shell then executed for you. So here's some examples, some command lines, and to kind of, just kind of jog your memory and stuff, right? Like here's like a copy command. Remember, sometimes some commands take options, and then they usually take some file names and stuff. Like this is a copy command. This shows me files in a directory. This searches for a file for things that match patterns. Remember regular expressions. You may have used programs that aren't part of Unix, but are part of your sort of discipline. So mostly here in QC Bio, we're bioinformaticians. So, we're, sequencing data is the big thing, for the last decade. So, like SAM tools is one of the things you use to manipulate alignments, right? When you align reads from a high throughput sequencer to a reference genome, you probably get a BAM file out. Well, SAM tools is like a very important command line utility, not part of UNIX, but sort of part of the bioinformatics kind of consensus. It's a freely available tool whose job in life is to manipulate BAM files. You may have software that you compile and install yourself and use that. We're going to talk about shell scripts, which are basically ways of putting shell code inside files and then using them repeatedly. And then you can make pipelines where you sort of you use multiple programs, but then you wire them up together. So one of them's output is talking to another one's input and so on. We'll get a lot into that in this workshop. And also there's redirections, which, they're kind of maybe the things you usually see at the edges of pipelines when you want the first program to read from a file or something, or the last program to write to a file or something. All right. So yeah, so kind of give you maybe, you probably have some intuitive understanding of kind of what the command line looks like. Let's do like a little bit more about the actual details, the full rules. So yeah, the first word is kind of the program name, and that can be interpreted in different ways. We'll talk about that in a second. Then programs get 0 or more arguments, right? Then these things that follow here, this particular command has 3 arguments. Those arguments are basically completely freeform. The operating system itself and the shell itself don't really understand anything about those. The shell's job is to just sort of isolate those, maybe do some text substitutions, transform them a little bit, but basically they just get passed to the program, and then the program does with them whatever it likes. And so, the interpretation that the fact this starts with a hyphen and it's got all these letters doesn't mean anything to the shell, doesn't mean anything to the operating system. But the CP program, that's the thing that defines the meaning of this thing. And each program thus has to have documentation and so on that tells you how it interprets its arguments. So of course for CP, the rule is the thing that doesn't, things with dashes are options. Things that aren't, the first one is the source, the second one is the destination. There can actually be multiple sources, but the last thing is always the destination. And then the options have a particular rules, which we'll talk about in a second. Remember that the command lines are generally case sensitive. You can't do capital C, capital P, whatever. Everything's case sensitive on Unix generally. File names, command names, everything. Options, everything. And remember, there's no undo generally. You type a command, it runs, it does what it does. All right. If you ask it to delete stuff, it's gone. Okay, whatever. There's no undo, backup, or whatever. This is as you tell it to do things, they are happening. Okay, that's the way it works. There's a general philosophy that Unix has, which is to provide lots of these little tools, right? Like sort and cut and cat and head and tail and whatever. And the way you get more complicated things done is by putting those together, rather than making sort of like one mega program that sort of does everything, right? So we solve larger problems by basically composing smaller pieces. And then the shell features and the design of the operating system, things like the redirection pipeline, are the things that make that composition easy. Generally, plain text is the way programs read and write their output. I mean, obviously there's binary files around, and things like the BAM files and so on are binary and so on. In that case, you generally need some dedicated tools that work on those binary formats. But most tools, unless they have good reasons not to, read and write plain text, because that's sort of very easy to work with, and humans can look at it and so on, and it's very powerful. So even in fact, BAM files, one of the things that you want to do with them, you want to pull out alignments or make changes or something. Generally, the way that you would work with that is you use some tool that expands that back into some text-based format. Like BAMs are really SAM files that have been compressed, and SAM files have a lot of columns, but they're just sort of a tab-oriented grid format. So you use some tool to expand that back into text, use base Linux utilities to manipulate that text, and then SAM tools again would recompress the output back into a BAM or whatever else you're writing. Maybe you gzip it into another file or something. But basically, yeah, a lot of even if the stuff you start and end with is a binary file, the intermediate stages are often plain text. And it's designed that you can sort of build things up sort of incrementally, and so on. We'll see examples of that in a as we go on the next 3 days. And so it's not like you just sort of like write a lot of code and then debug it and so on. No, you should be kind of like getting your things working in pieces as you go. It makes the repetitive tasks easy to automate. And, don't get overwhelmed with all this. Even, all the new features we introduce here and so on. You can be surprisingly productive with surprisingly small subsets of this stuff. But as you do learn more, it kind of becomes synergistic and you kind of level up and are able to be more productive at faster rates and stuff. But yeah, you can do a lot with even sort of fairly small subsets of this stuff. All right, here's a more detailed view of exactly what the rules are for command lines, okay? The white space has to separate the program name and the arguments from each other, and you can have extra white space on the front and back. White space can be whatever, spaces, multiple spaces, and so on. It doesn't matter. They're just used to decide how to break the thing up into the words. The first word is the program name, and there's rules for how to interpret that. Like, we'll talk about the path, we'll talk about shell scripts and stuff, but there's various things that this can be. It can be kind of just a name that the shell then has to go and figure out what file on disk that really means. You could actually give a path, a local path, a relative path, or an absolute path to explicitly name what you want. Or there's other things that can happen too. We already talked about the arguments being very free form. They can actually be completely arbitrary strings. They can't have what are called null characters in them, but basically they're arbitrary binary strings. It's a little hard to type things that aren't text into the shell, but the operating system supports it, and there are ways to do it. Those are basically just an array of strings, just a list of a few strings that are just completely arbitrary binary strings, and the program interprets them. The shell helps you out because a lot of times directly specifying all the arguments in their full detail is kind of painful. Like you want to run something on a lot of files or whatever, you don't really want to type all the file names out. So the shell gives you a lot of features, which are one of the things we'll talk more about. You've seen some of them already. Like you've probably seen the asterisk in Workshop 1A that does the file name expansion. Like you can do like star.txt and that expands into a list of all the text files that are in your current directory and stuff. So that's an example of one of these transformations that the shell does, where before it hands off the arguments to the program, the shell will transform them according to the rules of the shell language first. And those are features to help you kind of work more efficiently. So that's stuff like the path name expansion with star and question mark and some others. There's all these $ expansions, which you probably haven't seen any of yet, but these are related to shell variables and stuff, which are very important. Brace expansion, tilde expansion. There's something called process expansion. There's arithmetic. The shell can do arithmetic. That's often helpful when you're scripting stuff. Like there's 7, but we ask the shell to do the arithmetic. There's all kinds of stuff. There's escaping. That's something we have to talk more about. You probably saw some of that in Workshop 1A. Like you sometimes have to control the division of things into words, right? Like if you had a file name whose name was a space b.txt, and then you wanted to do like this, that's not going to look at that file because this space serves to separate this argument from this argument. And that's 2 arguments to cat, not a single argument, which happens to have a space in the middle of it. So maybe you talked a little bit about quoting in Workshop 1A here. You got to put some kind of quoting here. Double quotes would work in this case. Single quotes would work in this case. The main problem is that space has to not separate the words. Another way to do it is like this. There's all kinds of ways to do it. We'll talk about quoting more as we go, kind of as needed. But yeah, there's some parts of the shell language that are just there so that you can control the division into arguments, and quoting is all about that. Then there's all this grouping stuff, curly braces, subshells with friends. We'll talk more about later. There's scripting stuff, which we'll talk about, things like ifs, for loops, while loops. There's these case statements, shell functions, and then you can do the pipeline stuff. You may have seen in Workshop 1A, stuff like you might have had a file, something like this or whatever. You had things with pipelines. There's more characters there that do it. We'll concentrate on just this pipe symbol here, but like I say, we'll get into kind of pretty interesting applications of that. There are comments. Anything with a hash mark to the end of a line is a comment that's useful in shell scripts. And sometimes we have to type very long lines. I'm gonna swing that out of the way. So if you're typing a long command line, now notice that we just wrapped around to the next line, but we didn't hit return. That's still one command, and it's just getting longer and longer and longer, right? When I finally hit enter, that's the end of the command. Sometimes, especially on the slides and stuff, you can't tell on a slide whether that wrapping to the next line is with just like a space and continuing a single command, or whether that's a return and we're starting a new command. So oftentimes what you do for really long commands is just you put a backslash at the end of a line and then continue. That backslash means this line is not complete yet. We're still going. And so you can build up multi-line, line commands with this backslash stuff. And on the slides, I will generally show it that way because that makes it unambiguous, kind of what long lines are single things and what ones aren't. Okay. All right. This is you probably know some of this kind of intuitively, but let's talk about it more explicitly. And we're just using the date command here to illustrate sort of the general things that almost all Unix programs kind of follow these kinds of convention. So the date command, maybe you saw in Workshop 1A, it just gives you the current date in a particular format. So if I wait a few seconds, now you see it's 14/6/19 instead of 14/6/14. That's often useful in logging and stuff in scripts. Like you're going to start a process where you don't really know how long it's going to take, but maybe you want to know how long it takes. So you date and then do your stuff and then do date again, and then you can subtract, and now you know how long it was. That's especially useful in scripting because like you're going to run some long thing. You don't want to sit there waiting for it, but you also kind of want to know for the future, how long does this kind of process take on average? Well, you just do a date, do your stuff, do a date. And now you kind of can come back later after it's done and say, oh, now I know how long it took. All right, but date actually, you may not know, but date actually takes a lot of options, okay? So if I actually do date help, you'll see it actually has so many options it scrolls off the top of the screen. A lot of programs support options like help and so on, and they give you sort of a summary, very condensed summary of kind of what they take you. And here you see there's all kinds of options that it has and so on. Some of the options are very complicated, like this. There's one of the format options, like it must be down below. Anyway, don't worry, we're not really interested in date per se right now, just the idea of how programs work. There's also man pages. Maybe you've seen those. If you say man and then a command name, you may get a help page that kind of is a little bit longer than the built-in help, a little more prose-like, but these are usually pretty compact too. To be honest, when you're learning stuff or new, a lot of times Google or ChatGPT or whatever is going to be your best bet because it's going to give you results that are a little more chatty and so on. Once you're kind of used a tool a few times and just kind of want a brief reference because you're like in the middle of composing a command or something and now you want to look something up, that's when these things like this and the man page are more useful because you kind of already know what you're looking for. You just forgot the details and now it's a good reference. But for real raw discovery, you may need a little bit more of a tutorial style stuff, and that you'll get from the web. But if these man page things, hopefully you saw less to view large files. This man page thing is giving you the man page in less. And so B to go backward a page, space bar to go forward a page, arrow keys to move around, and so on, Q key quits, and so on. Hopefully you saw the less command to look at files. If you haven't, we'll do less in a second. But the point is that there's all these options and there's kind of different kinds of options. Some of the options you see start with double dash. These are what are called long options. These are when the name of the option is a whole word, like multiple characters. Other options are just a single letter, and they usually start with just a single dash. Some options come in both flavors, like this double dash reference equals has as a short form -r. So sometimes these are nicer to write down just because it kind of makes it more obvious when you go back and look at the command later what it means, but it's not as fun to type. So oftentimes once you kind of get used to a command and know its options well, you just switch to all the short one letter ones rather than use the long form. So like here we're using one of the long options to date. You see that changed the output format a little bit. Here we're using one of the short options to date. Okay. This happens to be the same option, those two, that -R and this thing, whatever. Again, we're not really worried about what we're making date do, just the fact that their long and short options exist, and lots of programs use this kind of convention for their options. We saw the -help. Sometimes programs use -help, especially like Python programs. A lot of Python programs don't really appreciate the kind of the Unix conventions, and they just sort of make their own up. So they kind of use a long option, but they only put a single hyphen in front. The reason why we kind of have the long options and the short options with double dash and single dash is because the short options, most programs let you combine them in a nice way. So for example, here's another short option that date supports. And we know about the -R one as well. And if we wanted them both, we could do that. But short options usually allow you to pack them all together. So like short options let you do that. It's the same thing. It means exactly the same thing as -u space -i. Because you now see the reason for long options starting with the double dash, because otherwise you wouldn't know, is that supposed to be -r, -f, -c, whatever. You have to disambiguate the two, whether you're allowed to kind of take these apart one character at a time or not. And the double dash is how the convention for that works. Let's talk a little bit more about the quoting. So, for example, date actually supports things like this. If you look at the help page, but you'll see something went wrong there. And it's because the thing that comes after the, this is all supposed to be one argument. And because of the space, it takes it as two arguments. So sort of date's complaining to me because it's like, I don't understand this. And it hasn't even got to this point yet, because already by this point, it sort of says something's broken. So we need to protect that space. And so we could quote that whole thing. The double quotes stop the shell from considering that space as a separator. We could have just put the quote around the troublesome part itself. We could have put it here. There's all kinds of ways we could have done it. From the dates program's point of view, those are all exactly the same. Literally zero differences, because the shell thing is the thing that takes all these quotes and whatever and transforms them first. Date will never see these quote marks and stuff. Those are stripped out before date even sees them. So yeah, so all these things are completely equivalent. We're basically, we had to get the single argument of 18 characters into date, and that's, we just had to express to the shell what we wanted, because the shell default would be to split the arguments there. What else? Some arguments, if you repeat them, they don't do anything bad. Like that's basically the same thing as this. The U doesn't do anything if you say it more than once in this case, but for some reason the capital R here doesn't support being listed multiple times. Some programs, if you have a certain option and you list it multiple times, it's like the last one that whatever you do, the last thing is the one that matters. Some of them it's the first time, whatever, the programs just vary. We can ask the shell where it's finding the date programs. So date is actually in a file called user bin date. That's because when you don't tell the shell how to find a program, like most of the time you don't, you just give the program's name. What's happening is the shell has a variable. We haven't talked about variables yet, but this $ bracket notation is how you get the values of variables. So echo, echo is this command that just repeats what it's given, right? Right. No, see if you spell it right. Okay. So echo gets 3 arguments, and it just prints each argument separated by a single space. I happen to type here multiple spaces, but they don't come out multiple spaces because the shell just turns that into 3 arguments, and echo is the thing that adds a single space between arguments. If I really wanted those spaces there, I'd have to, quote them so that echo only gets a single argument with spaces embedded. So one thing echo is useful for is seeing what the shell has done to your command line. So here's a command line. We don't really understand what this is doing yet, but by putting echo in front, we can see what the shell transforms this into. And you can see this has got some long, complicated value. And these are all the directories that the shell is currently searching for programs. So when you say date, it starts at this directory and says, can I find a date file in here? Oh, no. Okay, then I will go to this directory. You see, it's separated by colon. In fact, if I pipe that to TR and change the colons to new lines, it'll be a lot easier to read. So basically, here, it's just going to go down this list until it finds it. And the first place it finds it is in user bin, which is one of the things on my path. That is how the shell finds programs. And when we get to shell scripts and stuff, this will be important because, for example, the directory where we write our shell scripts probably isn't in your path. And so then we can't use this mechanism of just typing the name of the program. The shell's not going to find it, and we'll have to be a little more explicit. Or we could manipulate the path. But one of the things, especially when you use third-party software and stuff, like SAMtools is not currently something in my path. But we're going to want to use SAMtools. And so then it turns out SAMtools isn't on Hoffman, but it's not part of your default path. So we'll have to talk about how you like add it to your path and stuff or whatever. But that, that's all just previews for the beginning. Let's see. Here's my first point where I can actually tell you that the different forms of quoting vary a little bit. If I use the double quotes, you see that still expands. But if I use the single quotes turn all the shell magic off. Single quotes are always literal. Everything in between is literal. Double quotes still let some substitutions happen, double quotes are mostly about stopping spaces from breaking up arguments. So that's just the barest difference between double quote and single quote is just single quote turns everything off. Double quote mostly just stops things from breaking up into multiple arguments. Still lets a lot of transformations happen. All right. But what we just did here with date, it's pretty much the same with every program. A lot of them have short options, a lot of them have long options, and they just handle everything the same with the same convention. It's just a matter of what are the options and what do they mean, what do they do, and so on. But in terms of the structure, just kind of like the overall structure of commands and stuff, it's basically the same for everything. Okay, in Unix, everything is a file. The file is the main way Unix talks about data, and files are just sequences of bytes. Bytes are just integers from 0 to 255. Okay, so binary, just binary sequences of data. Everything, your alignments, your plain text, your programs, executable binary programs, shell scripts, it's all just streams of bytes. The interpretation of those bytes matters depending only what program is going to get them. The operating system imposes no limits on them, and so on. So things like network connections, whole disks, and so on, everything in Unix is a file. We don't have to care about most of these kinds of files. We're mostly going to use just ordinary files. But this abstraction is very useful because the way programs kind of work with files on Unix is that they only manipulate files with very simple operations. So we're not really going to write programs in C or whatever, or Python. You might do that in another workshop. But when it comes down to it, when you start writing programs in traditional languages, the way they interface with files on Unix is by very simple operations like give me the next byte. Here is a byte, put it into the next place in the file. Either make the file longer, or if you're in the middle of the file, you're just going to overwrite it like that. Go to this place in the file. Is there anybody else writing to this file? Stuff like this. And what that means is that programs generally do not need to care at all about the details of the files. Like, is it a disk file? Is it a network connection? And so on. It doesn't matter. Because the way you're manipulating with that file is always the same. Give me the next byte. Give me the next byte. Give me the next byte. Here's a byte. Here's a byte. Here's a byte. It's the way they work. And that's how things like the pipeline stuff works and like the redirection operators work in the stuff like this, is because since the interface to programs and between programs is all of this type, it makes it very easy to plug things together. Because if we've got a program that's doing things like write byte, write byte, write byte, and a program that's doing things like read byte, read byte, read byte, we can just connect those directly together. And just have every time this guy does a write byte, oh, that's just because this guy's read byte. So this is how the composition works and stuff like this. And so the programs don't generally need to be very aware of sort of their context or so on, or is this a disk file or a USB stick or a video camera? It just doesn't matter. Everything's just a stream of bytes, and that's the way programs use it. Obviously the interpretation of those bytes often matters, but it's up to the program to decide that, right? So, okay. So you should have talked in workshop 1A a little bit about the file system, right? So there's the root of the file system. So here I'm on login 4. I'm looking at the root. These are the files at the top level. And you see this on the slide, this sort of the outline. Now there's millions and millions and millions of files on this machine and whatever, and that's perfectly normal. We only care about a very few places in here. But conceptually, the whole system is just start at the root, and there's directories below that. Each directory has subdirectories and so on. And inside directories are files. And the whole system, millions and millions of files, is organized like that. And so some of the directories we care about. So when you first log in, you're going to be in your home directory. For me, that's uhome c cocos. Okay, so we just looked at the root directory, and here you see that u, right? So if I looked inside u, there's home. And if I look inside uhome, there's this. And then uhome c, there's this. These are all the usernames that start with C in the system. Okay, there's a lot of them. Another place that you probably talked about in workshop 1A was your scratch space. For me, that's u scratch c cocos. This is your home directory does not have room. You have a small quota on your home directory. I think 40 gigabytes these days. Can't put too much data there. The scratch directory is unlimited. But the problem with Scratch is it's not backed up and things can disappear kind of without warning. They usually try to warn you when they do it. Usually it's at the maintenance times. Like if you've been around campus for long enough, you've gotten messages from Hoffman that say winter maintenance or whatever. We're reformatting the Scratch system as part of that or whatever. Then everything in Scratch disappears. But the main advantage of Scratch is that it's not limited. So oftentimes the way you end up working on Hoffman is you have your storage on USB, hard drive, your local laptop, external hard drives, cloud storage, data storage, Google Drives or whatever. You keep your big data outside Hoffman because unless your PI has kind of been nice and bought you a lot of storage on Hoffman, your storage on Hoffman is probably limited. And so often the way you work is you take your big data, which you're storing outside of Hoffman, you copy it to Hoffman, you process it for a few weeks or whatever you're doing your project, and then you copy results back out. But you don't, and you're doing all your work in Scratch because that's where you have the big space. For me, I actually have some project space that was paid space. That's a new project MCDB. And then that's all of us. We each have our own directory in there. And then I'm U project MCDB focused. That's paid space that has to be paid for every year. If you want to know what space you got, you can say my quota, and that'll tell you what your quotas are right now. So if you do that right now, you should see that, for example, I have on U project MCDB, I'm using 113 gigabytes. The quota is 13 terabytes. That space is 72% full between me and all the users. Obviously, I'm not using very much. I'm using 0.1 terabyte, and the space is 13 T. And my other quota is on U home, my home directory. I'm using 25 gigs. The quota is 39. So I'm 2/3 full basically on my home directory. But you see, there's no entry for Scratch. Scratch is not under quota. Files in your project directory and in your home directory are backed up and so on. They will not disappear on you underneath you. So yeah, so this is kind of, if you have some time and want to look at this, you can just see the outline here. But the main places that are of concern to us are U home stuff where your home directories are, U project stuff where your paid storage is, and U Scratch where your Scratch space is. All right, you should have gotten familiar with file names and path names. So if you look around in your home directory, so maybe you did ls. I always like to do ls/la. That gives you the long listing. So that's the difference between those two. Here you're just seeing the names, but with la you're seeing sort of the full details. We'll talk more about these details in a minute. But you should have some stuff in there, I assume, because you've logged into Hoffman before. You've done maybe a little bit. You had Workshop 1A. You maybe make some files and stuff. These are what's in my directory, and like there's you can give the absolute paths to things, right? You can always start from the root. U home C Cocos. That's what I'm looking at right now. And then if I looked in my desktop, I don't know if I have anything in my desktop. I don't. Do I have anything in here? Yes, actually, something. Okay, so there's also some dead symlinks. Don't worry about those. But here I'm looking at a subdirectory of my home directory, and actually I have directories inside there too. So I could look inside another level, and now I'm looking inside that thing, and I could keep going, right? Whatever. Actually, I got nothing in that one. And then some of these have. This is now a file and not a directory, right? You can see because this has got a D and this doesn't. And then you probably learned things like the cat command to be able to see the contents of the file and stuff. Or maybe you learned less, which is how you see bigger files, right? This is a small file, so it fits on one screen. But maybe if I look inside that directory, do I have some bigger files? Yeah, I've got this FASTA file scaffolds. So if I cat that out, that's a bigger guy that's gonna kind of go by, but I could use less, and now I see it a screenful at a time. So yeah, so you learned about how to specify the path to things. This is the most simple form, which is to give what's called the absolute path, start at the root and give the entire sequence all the way down. But one of the things you also learned is that there's a context, right? What's called the working directory, current working directory. PWD shows you the current working directory of the shell. That's my home directory, uhome C Cocos. So if I type a path that doesn't start with slash, it's as if I had this on the front of it automatically, right? So I could take this thing that we just looked at, but since this is the same thing as my working directory, I can just go from here, right? So this this here. I'm going to copy and paste. So this is now a relative path. It's a path that starts at the PWD and then the current working directory and goes from there. And ls can find it, less can show it, works the same. In general, this slide gives you the full rules for what are called path names. So if you start with a slash, you're starting at the root. If you don't start with the slash, you have to put your current working directory in front. The current working directory is a Unix context that every program has their own working directory as part of their context. The one that matters most for us is the shell, because when the shell starts a new program, the program it starts gets the same working directory as the shell does. So if you want to control the working directory of a program, you change the working directory of the shell, so that when the shell starts the program, that program gets the same working directory as the shell did at that moment, right? So you're coming along, you change the directory in the shell. Now you're here. You start a program in the shell. That's over here. This directory becomes this guy's working directory. If this is a long-running process, we haven't talked about how to kind of. All our interactions with the shell so far have been where the program has to finish before we get control back at the shell. But there are ways to let the shell come back before a program is done. So if this program was long running, and then we change the directory here again and started another program here, that doesn't do anything to this guy. This guy got the working directory change at this moment, but then they're not connected anymore. The shell changes to a new directory, shell starts a new program. This program now has the new working directory, but these two are independent. The full rules are basically, yeah, so if you start with a slash, it's absolute. If you don't start with the slash, you put the current working directory on the front. And then in a directory, giving the name of a file inside the directory moves down to that guy. And then ... moves you back, and .. stays where you are. And then repeated slashes in a row don't mean anything. And directories are allowed to have an extra slash at the end if you like. So these if this is the situation where you've got root A and B directories, and inside A there's CDE, and inside B there's FG, and your working directory is pointing here at this guy, all these paths are exactly the same path. So root AD is this guy right here. Or because the working directory is already pointed here, I could just say D, that's the same. I could say /D because the working directory is here. Dot takes me back to the same place where I am. Then I go down to D. Or I could start with an absolute path BF. I could double dot, which goes back up to B. Then I went down to G. Then I did 2 more double dots. That goes back up to the root. Then I did a single dot at the root, which stays at the root. Then I did a double dot. Well, the root's its own parent, so you don't move anywhere. You're still at the root. Then I did 3 slashes in a row, which is the same thing as a single slash. Then I did A, D, back up. Well, now we're here. Then D, and then 3 slashes. It's all the same. We end up at D. It's the same thing. So it's not it's a stupid way, but that's the rule. Sometimes these are less stupid. You wouldn't have one this stupid, but sometimes. But these are the rules. Okay, so that's how you transform any path name into what it actually means. All right. And we've already navigated around, and you should recall from workshop 1A, right? PWD, that's where my current working directory is. LS, that shows you the contents of, without any arguments, of the current working directory. If you start giving arguments to LS, then it's going to show that and not the working directory. LS has tons of options. You probably didn't realize that it has so many. It has a nice man page. It can do things like recursive listings. So like, let's look at my Scratch directory. This is where lots of files are for this workshop. So my Scratch directory is uscratch tokens. You can look at that. That's world readable right now. And it's got 3 directories in it. But those 3 directories themselves have tons of subdirectories and stuff. And so if I did LSLA, that'll give me the long listing of those. But if I add the capital R, I'm asking for what's called a recursive listing, which means that for every directory that you list, also go inside that directory and keep listing. And this is going to be long, so I'm going to Control-C to abort that. You see that stopped early. And then I'm going to pipe that to less. So here, LS is producing output. We haven't talked about standard output and standard input yet, but LS is producing output, and the pipe redirects that output to be the input of less. And so now I'm looking at my directory listing 1 page at a time. Now I can space, I can use B to go back, and so on, and I can look at it a little bit at a time. And you see there's lots of files, lots of directories here. lots and lots and lots of files. In fact, let's how many files how many kind of lines of output am I seeing? Not quite the same as a file count, but we could pipe the output of ls to word count. WC is maybe a utility you saw. WC with an option -L counts lines. So here ls is working, you see it's actually taking a few seconds there because ls actually produced almost 48,000 lines of output there. All right. Yeah, question? Yeah, that's a good question. So one more slide, right? Because I think you talked about permissions, but let's it's such an important topic. We'll talk again about permissions. Yeah, and you also should have seen in workshop 1A how to look into files like cat and stuff like this. So let's do a little jog your memory there. I'm going to change directory to my scratch directory. You can do the same CD command so that you're looking at the same files. You know, we want to stop typing it so much all the time, right? So that's a lot to type. So we'll just CD there. So now our working directory is in my scratch directory. And let's go into, say, the workshop 6 directory. So here's another shortcut, which you probably, hopefully you covered in workshop 1A. If I just type the W and then hit the tab key, the shell will will look at the files and try to give you the longest unique completion of that. So if I say W and hit tab, it actually types workshop for me, because while there are multiple options for how that goes, all of them start workshop. So the shell has typed as much as it can before there's a decision to be made. That's called tab completion, and is super helpful for typing long things. So if I now type a 6, there's now only one way to complete this. So now if I hit tab again, it'll type the rest of it for me. That's super helpful for long things. So here I did a CD with a relative path. So I changed my working directory with a relative path. So now I'm in this place, right? Okay. So here's another way to get around it, is because you are using a graphical terminal emulator. You can highlight things with your GUI. Use your GUI clipboard and paste things, right? So if I wanted to see inside that file, now I can GUI paste and type it that way too. That's another way to type long things and stuff. All right. So this is, you just saw it with cat. It's a fairly long file. I could use less to look at it and look at it a page at a time, but then there's also commands like head. Probably you saw head, that shows like the first 10 lines by default, and there's tail that shows the last 10 lines by default. Those take options. So like if you ask head for help, you'll see that, oh, if you do -N, you can control the number of lines. So like I could do -N3 and I would get only 3 lines at the top or whatever. So, you know, cat, head, tail, last, these are ways of looking into the contents of files. Here's your permissions question. Yeah, why can you can currently see everything in my scratch space if you kind of start poking around. And that's by intent. And the reason is because I've set the permissions up to do that. And hopefully you talked a little bit about permissions in workshop 1A, because I mean, you know, you don't want your stuff to be deleted by somebody else, or I mean, you want control over who can see your stuff and, you know, who can, you know, change your stuff and stuff like that. So that's one of the reasons why I always recommend the -L option to ls, because it always shows you that information. I also kind of just like the one-line per file format of this -L. I just find it's easier to read than these sort of multi-column things that. But what ls with the -L option shows you is the owner of the item, the group of the item. This is the byte size of the item. This is the last date it was modified. This is what type of file it is. Most of the ones you care about are D for directories and dash is for ordinary files. And then these are what are called the permissions, which we'll talk about right now. But basically, my ID on Hawthorne, if you type ID on Hawthorne, you'll see who you are. So I am user ID 9271, but everyone, you would just use the name, which is Cocos. I am part of my primary group, as it's called, is Mateo P. That's my PI. But I also belong to the group MCDB. So this is your primary group, but then you see group SQL, and you might have multiple entries here. These are a complete list of group memberships. So I'm also in the group MCDB. That's my department. And so this is this and this is this. Then these little letters here, each of it just is a bit. These are really just zeros and ones, but the order is always like this. So instead of writing zeros and ones, they help you out by kind of jogging, remembering what the interpretation is. The R's are related to read permissions, the W's are related to write permissions, and the X's are related to execute permissions, but how that works on directories is a little different. And then the three groupings, you see there's kind of like one RWX, another RWX, and another RWX. The first one is for the owner, the second one is for the group, and the third one is for everybody else. So, all right, we just talked about this. We're talking about the permissions, right? So the green is for me, the yellows are for the group, the reds are for everybody else. And it's always the first one that matters. So if you match the user, you are the user, and the first 3 bits are what matter to you. If you aren't me, but you are in the group, then the yellow is what matters to you. If you aren't me and you aren't in the group, then you're in the red class. Okay. So if there's an R here and it's an ordinary file, here's the little cheat sheet. Okay. For ordinary files, it's this column. For directories, it's this column. The R versus a dash. If you have the R, you can read the contents of the file. If it's a dash, you can't. If the W is there, you can change the contents of the file. And if it's a dash, you can't. And if an X is there, you can run the contents of the file as a program or as a shell script. Don't worry about that yet. We'll get into that once we get to shell scripts. For directories, it's a little different. For directories, the R is to whether you can get the names of the things in the directory. The W is whether you can create and delete files in the directory. And the X controls whether you can go through the directory. So for example, to CWD into a directory or to follow a path that goes through the directory to get to the other end of the path, that needs the X of every directory in the middle of the path. So for example, if I want to stop you from seeing what's in my scratch space, so here, let's look at U scratch C, and U scratch C focus. That's the entire path to see into my scratch space. Well, let's pick a file in there too, just so that we kind of keep going a little bit. So then let's pick this workshop 6 directory, and then we'll pick some file that's in there. Right? So this is now an endpoint, if you like. Okay, so that's that, and now I got to do all the intermediates, right? So that's the directory there, and then there's the file itself. Okay, so that's the entire path to get to that file from the root. The root, you see, is owned by root, but it's got, so none of us are root. That's the super user on the system, and none of us are in the super user group. So for these first few, these are the ones that apply to all of us. But they've got R and X on them, which means that we can see the file names in there and we can pass through there. So that's all good. We can go through the U. In fact, the root is actually a level 2. So to be really complete, this is the full path. All right, so RX here with root, RX here with root, RX here with root, RX here with root. None of us can add or delete files in any of those places, but we can sure list the names of files in there, and we can sure pass through them on our way to find things. No big deal there. This is the first directory that's under my control because I'm the owner of this directory. Now you're not me, none of you are me, and I don't think any of you are in Matteo P's group. So for you, the bits that matter are these 3 bits. And currently they're on as RX. So you can list the names of the files in there, and you can pass through there to get to things. If I took away that X, the X would be enough, but I'll take away the R and X too. So if I take away the other, take away the R and X from other at that place, now you look, so now they're gone. And now if you guys try to LS and stuff down there, it's not going to work. And because I've now taken it away from that top place, I do not have to take away permissions for you from anything below there. Because now that I've removed your ability to even pass through that point, you are now restricted from anything below there, right? It's very easy to remove permission from a huge group of things. All that matters to protecting my scratch space from other people seeing into it is to remove that X, basically, is the most important one. If I wanted to even hide it from members of my own group, not that any of you are in my group, I could also take away the middle 3 bits there. And now even people in my group can't see in there, right? So now this is just basically me. The super user, of course, can ignore all the permissions, but basically now only I can see inside my own scratch space. And did you guys confirm that? Did you actually play? Somebody played with it and says, oh, I can't see in there anymore? Yes? Permission denied. Yeah, exactly. That's the message you get. So now I'll put them back. So now I'll add group and other both get R and X. All right, so now you'll see that they're back. And now if you try again, you should be able to see back in it. So that makes it very easy to like, so I would right now, if you haven't already, you check your scratch space, you check your home directory, and you check your project directory, and make sure those are how you like. The safest solution is to just make it only RWX for yourself and dash for every, for the other group and other. That's just you. Of course, sometimes you do want to share files with people, right? So maybe you do need to share with your lab, people in your group, files, but maybe you don't want them to delete things. So don't give them the W, right? So you get the RW and maybe the RWX, depending on what it is. Like if it's your own directory, it's an RWX. If it's a file, it's probably just RW. But for people in your group, maybe you give them R-X or just R. You don't give them the W because you don't want them to be able to change. And for the other people, general people on the cluster, you probably don't want them to have access at all. So for that last group of three, you probably want dash. So this next slide shows you the common, there's all kinds of combinations that are possible, but I think these are the ones that make the most sense. So for files, you're looking at these. For directories, you're looking at these. The safest option is just stuff for yourself. If you want to share with your group, it's something like this. If you really want other people to see it, you might do this. I would probably never recommend putting a W in the for the everybody place. If you actually look on Hoffman, you will find that some people have either knowingly or not changed their permissions to be very permissive. So like if we look at U home C and just looking here, I bet we can find somebody. You see what Hoffman's default is. I think by default they create nothing here because that's just the only safe option. But if we look around, can we find? Oh, there we go. She's got RWX for everybody. And that means that any one of us could go into her home directory and start deleting files because we have that W permission bit right here. Don't do it, please. But that's not a safe setting, right? She's made it too permissive. She probably had a problem where she wanted somebody else to be able to interact with or something and give her files and stuff. And so she did this, but I wouldn't even do it for a second, but if you did it, you should just do it for the few seconds you need it or whatever. But this will solve the problem. Whoever else she was working with could absolutely give her the files or whatever, but so can anyone else in the universe and also delete things and stuff. So yeah, this is not a safe setting. But yeah, check the three most critical directories to check are the top levels, the home directory, your scratch space, and the project space. If you want to share, you have to get a little trickier, right? Because then you have to add at least the RX permissions to those directories. But then that makes everything inside those directories now be qualified for that. So now you have to kind of make sure that there's kind of a frontier, right? You have to sort of choose where your frontier is going to be and get the permissions correct on that frontier. Once you reach a point on the frontier where you deny permission, you don't have to worry about the permissions below that point because you've covered it. But whatever the open part is, how that oozes down, you got to know what that is. If you open up your home directory and you haven't kept your permissions in check there, and you've got kind of files with all kind of permissions in there, as soon as you enable other people to see into your home directory, then all those kind of permissions start to matter, right? So you should, whenever you open up a directory to be shared, you should inspect all the permissions at that point and kind of dial down any that are too permissive, right? And so you just kind of expanded your frontier down a level, possibly many levels if each of those directories has permissions on and so on or whatever. But it also kind of means that it's kind of a pain to add sharing where there wasn't sharing before, because while you can just remove sharing in kind of one place and it takes away everything below, if you have a whole big tree that you want, say, to make readable by your group, but none of the permissions are on those files, you got to add them to all the files, right? Because every single thing that you want to be readable by the group has to have that group permission on. It's not like you can just sort of set one directory somewhere and say, oh yeah, below this point, everything gets automatic R's everywhere. It doesn't work like that. It's only like, it's like if you have a directory with 10 subdirectories, each with 10 files, so there's 100 files down here, and you want all those files to be readable by the colleague. Every single one of those files and directories, top and middle, has to have all the permission files in yeah, check your stuff if you have it, because often we find people have set things in ways that they didn't expect. If you haven't, you kind of saw some of the syntax there. I don't want to, I don't want to spend forever on this stuff, and we got more interesting stuff to get to. Kind of, all of this is very important, but the syntax is kind of here. It's the chmod command is the one that modifies the permissions. You may have seen, depending on who your instructor for workshop 1A or what you've seen in the past. There's two. The examples I was giving, you saw some of the commands in here somewhere. There should be in the recent history. There's our dates. The chmod should be in here somewhere. I don't see it. So I have two windows open. No. Okay. Now, yeah, you see, I without even thinking about it, I use things like pipelines and so on. Whatever history is a shell command that shows you like the last 1,000 or 10,000 commands you've run, and then like I wanted to find the chmods in there because I wasn't. Oh, I guess they're there. I didn't see it right away, so I just piped it to the grep command, which is a command you should have seen in workshop 1A that looks for that word and puts out the lines with that word in it. And so actually there you see them pulled out. But I mean, once you kind of get used to it, you just sort of combine these things all the time. So yeah, so anyway, you saw this is the syntax I was using. It's kind of like you say who you're adjusting permissions for. U is for yourself, G is for your group, O is for everybody else, user group other. Then you can either say plus, minus, or an equal sign to either add, remove, or set permissions to. And then the thing that comes after that is the R, Ws, and Xs. So like this was remove from other R and X, remove from group R and X. For group and other, add R and X, right? I find this form kind of easier. There's also this numerical form, octal form that you may have seen depending on who you were learning from and stuff. So like if you, let me just make a new file here. So let's, I'm gonna go back to this is my Scratch-based top level. So touch command makes a new empty file. So there's a file A, right? And it starts with RW. You may have seen stuff like this, the numerical form. The last digit is the other, the second to last digit is the group, and the third to last digit is yourself. And then the R is 4, the W is 2, and the X is 1, and you add them up. So if you want RX, that's 4 plus 1 is 5, and so on. So if you see after that 644, now you see it's RWRR, because the 6 is RW, 4 plus 2 is 6. The R is 4, that's that 4, and then the next R is 4. But another way to have done that would be to say, set myself to RW, set the group to R, and set the other to R. It's the same thing. It just depends on kind of what syntax. If you're going to change all the permissions, I suppose this endures because this is easy. If you want to change all the permissions at once, it's short and compact. But in terms of semantics, it's sort of like this is much more kind of describes the intent. Anyway, that's the syntax for those changes. Oh, I suppose another thing to talk about is the default for new files. You saw that when I created a new file, and you can try this yourself, just touch a file, create a new file, see what permissions it gets. And you'll see here that the default permissions for me, at least, for new files are RW, but not anything for group, not anything for other. I think yours are the same, probably. I think this is the default on Hoffman, if you try it. For everybody. Oh, so you're RWRR. And is that actually all of you like that then? Yes? Okay. So that's good to know. So you're probably still protected because your defaults on your home directory stuff probably are RWX --. But good to know that actually your files are getting kind of created with everybody. That's controlled by something called UMask. So if you say UMask, this is a shell command. It's part of it's another context thing in Unix, like the current working directory. There's a context thing. UMask is a per process, Unix process context thing. Shell has one, and every program the shell starts inherits the shell's one. You see that my UMask is 077. Yours is probably 000. Yours is going to be what? 022. So that's actually the same settings as the octal stuff here that we did here with the 4 + 2 + 1. And it says the bits that are set in the UMask are the bits that are removed from new files. So for me, this 7 means RWX, and that means kill RW and X. So this is for the user, this is for the group, and this is for everybody else. So this first 0 means leave the RWX stuff for myself alone. For the next digit, which is the group, for me, it's a 7, and that's R + W + X. And that means kill RW and X from everything new. That's why my file doesn't get anything here. And this 7 at the end also means for other, kill RW and X, remove them. You've got you've got 2s though. 2s are W's. So that removes the right permission from group and other, but leaves the R and X. But for ordinary files, they're not going to be created with X anyway. So it's basically, that's where your R's are coming from, is the fact that your UMask has got the 2s in there and mine has a 7. So if you change your UMask, and like if I change mine to 022 like yours, and now I create a new file, you'll now see that my new file is like you. Anyway, so that's the rest of the story on permissions, is what's the default for new things, and that's controlled by your UMask. Let's see. Oh, okay, and well, almost a complete story. The rest of the story is only the owner of an object, only the owner of a file and the super user can chmod, right? You can't chmod somebody else's file to give yourself permission. And there's actually another command called chgroup, which you'll never use because it's only usable essentially by the super user. But if you were to chgroup, like you could change the ownership of a file. So like, I don't know, I need one of the usernames or something, but here's some other usernames on the system. So if I take like this guy or something, if I had super user permissions, I could change the ownership or something, right, and give it away to somebody else. But in Unix, actually, you can't give away files for good reasons, because injecting files in people's space can cause things to happen. So the way you share a file with somebody is to let them be able to read it, and then they copy it out from you. You can't push the file. Only the super user can chgroup. Chgroup changes the group. Chmod changes the permissions that you can do. Chown changes the owner, which you can't do. And chgroup changes the group, which you can do if you're in multiple groups, as long as you're the group owner. So for example, you saw that I'm also in the MCDB group. So although my primary group is Mateo P, which is why new files get created with that as their group, I can change group anything I like to MCDB because I am in MCDB. So I could change the ownership of like that directory to MCDB, and now its group has changed. And I can change it back because I'm a member of that group too. So yeah, so chown, chmod, you have to be the owner or super user. Chown, you have to be the super user. Chgroup, you have to be the super user or be a member of the group that it currently is. That's the full story. Okay, let's start getting into more complicated redirections and stuff. And for that, you probably saw in Workshop 1A very simple redirection. So for example, date by default prints to the screen, whatever that means. We're about to make this clearer what this actually is really doing, because we really kind of need to understand a little bit more about how this works to really understand how the redirection really works. And we need to understand how the redirection really works to make more fancy redirections. So anyway, so that prints to the screen, but we'd like to know a little bit more about that in a second. But then maybe you saw how to redirect that to a file, right? So then I can do this, and now it shows up in a file now, and the contents of that file are the output of the program. Okay, but kind of you have an intuitive understanding of that right now, but like to really kind of work with that, we kind of have to have not just an intuitive understanding, we actually have to know kind of what's going on. And the answer is that Unix programs have more context. There's tons of context. We've talked about the working directory, we talked about UMask. Here's another piece of context that each Unix program has, and that is what connections to files it has. Okay, so there are three distinct. They're just numbered 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. There are three distinguished numbers in that range that have, by convention, specific uses. File number 0 is what's called the standard input, or stdin. Okay, so this is this little section here. File 0 is standard input, stdin. I'll say standard input, but if I type in slides, it's stdin, it's so much shorter. It's easier the way to write it. And that is sort of by convention your primary or your main or your default input file. File number 1 is standard output, std out. That is your primary, main, default output file, whatever that means. As I say, it's a convention. So the particular exact meaning kind of depends on the program, but this is sort of the broad convention. You'll see some examples and kind of get the idea. Then file number 2 is what's called standard error, stderr. And that's kind of the same thing as standard output, but there's a reason why you separate standard output and standard error. And that's because, for example, if the program is doing some long complicated thing and it's part of a pipeline, or it's writing, you've redirected its output to a file or something, and then that program has something happen, an error, disk full, out of permission, something happens. If it tries to write its error messages to the same place standard output goes, you're very likely to miss it because it's just going to go along the pipeline. You know, it's like your error message is going to be mixed in with the regular data. You may not notice and so on. It's a bad idea. So it's a good idea to have sort of like the main data flow and sort of like the error messages not go to the same place. And so file number 2 is called standard error, and that's the default diagnostic process, progress, error messages go there. Okay. Most of the time, like for your all the time, you know, most of the time we're working due to the magic of SSH and the terminal emulator and stuff. So for the shell, if the shell, of course, has a standard in, standard out, and standard error. And then, of course, programs that the shell starts will, unless you say otherwise, inherit the shell's standard in, standard out, standard. The shells, with the magic of SSH and the terminal emulator and stuff and whatever, you start off with your shell's standard input coming from your keyboard, your shell's standard output going to your screen, and your shell's standard error goes to your screen. Okay. And like I say, unless you say otherwise, programs that shell starts, same situation. That's why when I type commands into the shell, it's coming from my keyboard. And when the shell prints stuff, like its prompt, that's going to my screen. And when the shell starts programs, that's why I see the output of date on my screen. Because date's standard output, date doesn't read standard input, but date certainly writes standard output. Where does date write its standard output to? Whatever standard output is when date gets started. What is that? The same standard output shell has. Because shell started date. What's shell's standard output? It's my screen. That is how date's output ends up on my screen. So what redirection really does is just tells the shell, before you kick off this program, please reconnect standard in or standard out or standard error to something else. So when we do this, instead of date inheriting the shell's standard output, the shell will arrange so that date's standard output is actually connected to this file, now.txt. It's the shell that creates the file now.txt. The shell opens the file now.txt for writing. It's an empty file now pointed to at the beginning. Then the shell kicks off date with date's standard output being that connection. So when date does its normal write a byte, write a byte, write a byte, write a byte, date doesn't care it's writing to a file or the screen or whatever, but date just does its little thing and writes its little bytes out. But because the shell has started date with date standard output connected to this file, that's where the output ends up going. That's how redirection really works. So, for example, here's a command, maybe you've seen it, maybe not. Seek just writes out lines between whatever numbers you get it. You know, like I could do seek 7 and 12, it's just going to give me lines of text 7, 8, 9, 10, 11, 12. So yeah, if I run seek without anything else, standard input is going to be my keyboard. Seek doesn't read standard input. Standard output is my screen. Seek does write to standard output. So that's where the output goes, is my screen. I can tell the shell, no, please redirect seek standard output to the file 1 to 10. Oops, and there it is. And that's what goes into the file. And in case you didn't know, if the file already exists, the greater than sign redirection in the shell first erases all the contents of the file and gives you back to an empty file again. So if I do seek 1 to 10, 3 to 7, and I also put that in 1 to 10, the file name is not going to be too good now, but you'll now see that replaced the contents, right? So it was an existing file, it got clobbered, as it's called, and we just reread from scratch. If you wanted to actually append, you actually have to say, so like if I go back to seek 1 to 10, okay, I wrote it over again, now it's back to the way it was. If I did 3 to 7 with double greater than sign, that's called append. And what and this is now an instruction to the shell. Seek has no idea any of this has happened. That double greater than sign means to the shell that not only should should connect the standard output of the program to the left, to this thing I'm going to give you on the right, but the 2 greater than signs means that if it already exists, just go to the end and keep going. Don't erase it first. So now if I do this, you see it's gotten longer rather than blowing away the contents that were already there. Okay. Now let's put it back to the way it was. Okay. In fact, not that it really matters. I don't think we're going to really have. We might have one occasion at some point to do this, but there's actually the shell takes a digit before the redirection operator that tells it which file connection to change. If I say that file connection 1 is redirected, that's the default for greater than sign anyway. You remember 1 is the standard output. So okay. So there it is, but that 1 is just not necessary because that's the default for greater than sign anyway. But just to prove to you that sort of it's file number 1 that kind of got reconfigured there. A lot of programs work in multiple modes. So like one very common mode of operation for Unix programs is what's called a filter. If they don't take any input, they just produce output on standard output. If they don't produce any output, they read their input from standard input. A lot of them also both take input and produce output. In that case, they read from standard input and write standard output. That's really what people do with a filter. So a filter reads from standard input, writes to standard output. We'll see a lot of those things like the shuff command, sort, and others. But a lot of those commands actually work in multiple ways. And if they have command line arguments that specify files, that's what they use. But if you don't mention any files, then they switch to the standard in, standard output set. So like shuff is one of these. So shuff is a randomizer. It reads all the lines of a file, randomly permutes them uniformly at random, and then writes the output. So where does the input come from? Where does the output go to? If you don't mention any command line arguments that are files, it reads from standard input and writes to standard output. If you do give it file names on the command line, it reads from those and doesn't read standard. And it actually has an option output file -o or long option double- output. And if you give it that, it writes its output there. It doesn't write the standard output. But you see now it can work in all combinations, right? It can read from standard in, write to standard out. It can read from a file and write to standard out. It can, what's the other way? Read from a file, write to standard out, and it can read from a file, write to a file. It just depends on what options you give. And a lot of Unix programs are like this. They support all those modes of operation. So for example, we've got this 1 to 10 file, okay? So with the number 1 to 10. So shuff, if I give it the command line argument with a file name, it's going to read that as its input, but I didn't mention the output file stuff, so it's going to write the standard output. So I'm getting a random shuffle of 1 to 10 on my screen because my screen is standard output. I could have gotten essentially the same effect by redirecting its input from the file. So here it is shuff itself that opens the file. This is just, the shell just passes this as an argument to the program. And shuff's interpretation of that is, oh, it's a file name, I'm supposed to read its input. But the shell has no business. The shell is not participating in this business with this file. Here it's the shell that opens the file. I've given shuff 0 arguments. And in that mode, shuff acts as a standard in to standard out filter. So here it's the shell that opens the file. This is an input redirection now. So this is a redirection of file number 0. In fact, you could actually put a 0 here, but nobody ever does. So the shell opens the file at the beginning, opens it for reading, And then when it starts the shuff command, it makes the standard input of shuff be that connection. So same effect, but slightly different mechanics. Is that here's the shell that did the opening. The file was opened before shuff even started. Shuff acted in standard out filter mode. Here it's shuff that did the opening and produced its output in standard output. Okay, the reason why this then gets more interesting when you start using the pipe operator and stuff. So now we could have just not had this intermediate file at all. So here we've got this intermediate file, sort of this 1 to 10 here. Suppose my overall goal is to just get a random permutation of 1 to 10. All right, then I don't really, why clutter things up with this text file, right? So let me get rid of them so that they're not even there anymore, right? So now I can do seek 1 to 10, pipe to shuff. And if you look, no files. What did that do? This is a seek, we know, is a standard out spitter, right? Okay, he produces output and standard output. This is a shell pipe operator. And what this means is simultaneously start the program on the left and the program on the right, arrange for the program on the left standard output to be connected to the standard input of the program on the right. Then this program is then producing output at some rate, and this program is eating input at some rate. There's a little bit of buffer there, but it's very small. And if shuff starts getting too far ahead, the operating system will pause it until the program on the left produces some more output for it. If the program on the left gets very far ahead in making output and the program on the right isn't reading that, then eventually the OS will just pause this guy on the left until the guy on the right starts catching up. So the operating system will, in general, try to keep them both running at the same time, but it will pause them as necessary to keep them in sync in terms of the reading and writing. And so this is pretty cool because it means we didn't have to have the intermediate file. The programs ran in parallel, and it's just more efficient and cleaner. And so here it's still not a big deal, but like when we get to like some real applications, this is really powerful, this setup, and the way Unix makes this kind of easy and stuff. It's sort of like you get this natural parallelism, and you don't have to always have like huge files on disk with intermediate stuff and so on. And it just ends up being a really great way of working. Not that this example is too small to really appreciate that, but you can kind of start to see the idea. So we could have had shuff write the output file, I guess, just to kind of complete the kind of different options you had. So like here, seek will generate the lines 1 to 10 on its standard output. We're still piping it to shuff, but then we're having shuff write an output file, okay? Because that's one of the command line options shuff takes. This is nothing to do with the shell. The shell just dumps this as a single argument to shuff, but shuff understands this particular pattern of argument to mean write your output to this file instead of to standard output. And so it shows up there. I don't really need the double quotes in this case. There's no spaces or weird characters there. That would have been just fine. For long options that take path names, I sort of do like to put kind of the quotes there just because it kind of visually isolates the path name. It kind of, you can see this a little better than with like kind of the equal sign kind of like jammed up in there, and you have to kind of parse this to kind of figure out where the file name is. But of course, the shell will just get rid of these double quotes before shuff will even see it. We could have done, shuff didn't have to support the output command line option because we always could have just done the redirection. Whoops. It's not the copy and paste I wanted to do. There we go. Okay, that's fine. Here, the shell opened the output, but some programs support options like this, some don't. But even if they don't, it's no big deal generally because you can always just do the redirection in the shell. Okay, we talked about the appending with a double greater than. Yeah, question? Not really, because they end up from the operating system point of view being about exactly the same. It gets more complicated if there's multiple output files. So some programs have like, a lot of bioinformatics programs might have multiple outputs, right? So like it's got like a BAM output, maybe a VCF output, and so on. And then the redirection, there's only one standard in and one standard out. So you can only kind of handle one that way. With multiples, you kind of got to have command line arguments or something, because otherwise you don't know how to say, like, there's only the input, the standard input output pipeline stuff. There's only one of those. So once there's multiple files around, you kind of got to have command line options to be able to specify all those, because it doesn't really. Does that make sense? Or right? Because how would you? I don't know what I mean, I don't know what the syntax would look like. Maybe you're imagining something like this or whatever, but that can't work because it's like these only do standard input and standard output. There's only one of those, so it's like, does this one happen and this one doesn't? Usually the programs like this have to have something like, they have things like things like this or something. They'll have multiple command line options, and part of the name of the command line option will tell you what kind of file it is, and then the file name there. So when there's multiple inputs and or multiple outputs, it's a little trickier. The multiple input situation can often be handled even with the redirection stuff. It gets a little more complicated. We'll see one like that maybe day 2. But multiple output files generally need command line options in there. But in terms of efficiency, not really. They're about the same. Another alternative to like that appending business, which is often nicer, especially if the stuff in the middle is complicated. So like you saw that, like, remember we did like this, and then like this, and then the second one overwrites the first one. So if you wanted them both, then you have to do this for the append, right? Another way to have done it is to use a subshell or command grouping. So the way that works is like this. You see the parentheses there. That's the difference. Okay. So what those parentheses do is actually starts another shell, which is exactly like my current shell, my current path. Everything is all exactly the same. And then the current shell, the subshell is going to work on this. But we've done the redirection in the outer shell all at once. So basically, this redirection is a redirection applied to the subshell. The subshell will itself create some more programs and stuff, but the programs the subshell creates are all going to inherit the standard in and out of the subshell. So if the subshell is redirected, all the stuff the subshell starts is redirected. So that's how this works. We start a subshell, we redirect standard output of the subshell to the file, and now everything the subshell launches is going to get its standard output redirected to this guy, because they all just inherit. And especially when there's a lot of stuff in here, you don't want to have to put like the redirections every single line and stuff or whatever. And so here you just basically, this is how you like redirect a whole bunch of stuff, right? Not just one thing. There's also a way of doing it without a subshell, which really doesn't, it just doesn't matter. This is command grouping without a subshell. Yeah, we should take a break. Let's, I guess Eli's got the sign up sheet. Let's take a 5-minute break. And I'll take any questions, and we'll pick up from there. Is there anybody on the Zoom yet? Nobody on Zoom. Yeah. It's probably hard to follow everything. You got the slide. That's what we're going to do. And we should do it. we basically thought a long time. Oh, okay. See on the screen. We have many classes. You get the little part in the middle and you say, oh, it's 10 candidates. So look at it, let's do this one. Good time. So you, so you, all right. So there's a huge leap between this slide and this slide. And it's sort of like, it's more just to give you a hint of what's possible before we're able to build something like this ourselves yet. So like, I still kind of just want to show this just so you can kind of see kind of where we're headed rather than just like explain completely how like this colored blob of text here, which is certainly by far the longest shell. This is one command line, right? It's huge compared to what we've seen before. But it shows you what you can do once you start combining the pipeline stuff aggressively. So suppose we randomly permute the numbers from 1 to 10,000. And then, so I mean, here's like a little small one, right? So like this is, I think, the numbers from 1 to 20 or something. But you randomly permute the numbers from 1 to 10,000, and then you ask, what's the longest sequence that goes up? Okay, maybe we're doing some statistics and we're trying to find the p-value for, we're assuming some null hypothesis or something, and we kind of need to know what the random statistics look like. So, it's sort of like, what's the longest part that stays in order? If you randomly permute numbers from 1 to 10,000. Okay. So like here, in this case, it's this green box part, right? Because this is, well, that's up, but then we go down, but then we go up, 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 up. That's pretty long. That's this run of 5 is all up. But then we go down, up, up, but that's shorter than that last green one. So that doesn't count. Down, up, down, down, up, down, up, down, down, down. But the longest up, that was this green stuff, right? So the answer for this particular run of the experiment, it would be 5 is the answer. The longest run of up is 5. Suppose we need to know what the distribution of this is, right? By chance, because maybe we've got some experimental result, and we want to know, is that possible by chance, or are we kind of clearly higher up than that? You know, like maybe our result came out 11 in the real experiment, and the answer is like, is that just normal for when you permute 1 in 10,000, or is that sort of unusual already? So one way to do that on the computer, I mean, if you know a lot of combinatorics and stuff, maybe you could calculate it directly. But one way to do it easily on the computer is you just simulate it, right? So you just write some computer thing to do this on a randomized, and then you run it like 10,000 times or 100 times or whatever, and you just see what distribution of numbers you get out, right? And that tells you kind of what the statistics are of the random case. We can do that with just kind of the stuff we've just seen with Shuff and all that kind of stuff or whatever. So like, here's the business. We haven't talked about shell for loops yet, but basically this red blob is going to run this code in the middle 1,000 times. And that's going to be the 1,000 repeats of the experiment to get the distribution. The orange code is just to print some progress information. Maybe I should just run this so you know what the output looks like before we talk about it. So big blob of text. There it is. There you're seeing our progress messages as we run 1,000 trials, just so we kind of know like when to expect it to be. I mean, otherwise you'd just be staring at a black screen and had no idea when it's about to finish. At least with that going by, we kind of know like, oh, it's not going to take that long. So it said we see 193 sixes, 628 sevens, 158 eights, 15 nines, and 6 tens. So if your experiment came out 11, that's kind of unusual. Right? We never saw that in 1,000 random trials. And so the p-value, as a guess, would be something like 0.001 or whatever. I'd say less than 1 in 1,000. So, all right, the orange thing is what prints this progress information here. That's not really important to the function. This is the actual meat. This is the code that generates one simulated run of the experiment. So there will be a single digit that comes out of this blob of code. And that will just be like, if this was the simulation, it would print 5 because the longest run in this simulation was 5. So what does this do? Well, the seq just generates the numbers from 1 to 10,000. Then we randomly permute them. That's a good start. That gives us kind of this row. We haven't circled the green part yet, but it gets that's the actual data. Now we got to find the longest increasing run inside this. There's a lot of ways we could do that. I think you saw the awk program in workshop 1A. Awk is another mini little programming language, but it's kind of good at sort of like things that are too hard to do in a shell script, but kind of like not really worth doing in Python or something. It's kind of like intermediate level. This is the awk program that we're running. And awk with no other arguments acts as a filter from standard input to standard output. So its input is going to come from this, and then its output is going to go to more places. Its job is to produce this next line here. You see my strategy. I'm going to look at adjacent pairs. And if they go up, I'm going to print a 1. And if they go down, I'm going to print a 0. Okay, so this is a 1. That's a 0. That's a 1, 1, 1, 1. That's a 0. You get the idea? Because now we transform the problem from going up to just runs of 1s, which is an easier problem. Okay. So that's the job of the yellow blob of code, is to transform from this line to the 0s, 1s line. And the way to do it, you remember awk has like the braces on the end control what lines that line of code applies to. And if you don't put any qualifiers, that runs on every line of code that goes into every line of input that goes into awk. We did a little if loop here. The NR is the record number, which is 1 on the first line, and then it counts 2, 3, 4 on subsequent lines. So basically, this blob of code runs on the first line, and this blob of code runs on every subsequent line. Okay, so what this does, on the first line, we just remember the value. $0 refers to the entire input line, and then this is a variable in awk. And so prev becomes equal to the first value. Okay. Because basically we have to, we can't know the first output until we see 2 lines. So basically we have to remember the previous line and then look at the next line before we can even tell what to output. So basically that first line, all we do is remember it. Then this is what happens in all the rest of the lines. This is the key part. If the current line is numerically greater than the prev, then we print that out. This in comparisons in awk, like most languages, C, whatever, Java, Python, the rest, Boolean comparisons produce 0s and 1s. 0 for false, 1 for true. So if the current line is bigger than prev, we print it's going to be a 1, and if it's not, if it's less than or equal, it's a 0. This you could probably just do with a print. You don't really need all this printf stuff, but it's a matter of style or whatever. It's not a big deal. And then, of course, to prepare for the next line, we got to change prev because, when we get to the third line of input, we need prev to be the second line. So this updates prev to be the current line, which would be the previous line on the next line. Okay, so this basically, this yellow code transforms this thing to this zeros ones thing. Well, we're getting there. Now we got to count the longest run of ones in this thing. So there's a utility called UNIX, and UNIX has an option -C. And that's a super useful command because it's essentially your key to making histograms and all kinds of things. So for example, if I make a little file, well, let me clean up here, get rid of some of these guys that we're done with. Okay, and let's use this as the example. Okay, so okay, I'm going to, I'm just using a text editor, a GUI text editor to do this because it's easier than typing it out directly. I don't know why I'm doing it like this. I don't think this leaves search and replace. Okay, there we go. So that's actually the example that's on the slide, just that we can kind of play with this. Okay, and I'm going to do a little thing here to make that be a file. I want to explain that magic. Yeah, that'll get us sidetracked if we try to explain that. But basically, I just made a file where it's just these guys, but one per line, just to simulate what would come out of the shuff, basically. Okay, so if I run this awk code and I give it, redirect its input from A and its output to B, we can kind of see what that little piece of awk code is doing. And you see here it produces the ones and zeros. Now I can show you what the UNIX-C does. So I'm going to do the UNIX-C, its input from file B, its output to file C. And what is in file C? And what UNIX does is it looks for lines that are the same that are in a row. And it tells you how many of them there are. So it said, I see 1, 1. Then I see 1, 0. Then I see 4 ones. Then I see 1, 0. Then I see 2 ones, and so on. You see how it goes? The first column is the count, and the second column is the repeated line. Okay. Now we're getting close because we now look at the lines where this is a 1. Each one of these now corresponds to a run of ones. The number in the first column is the length of that run of ones. And so basically we now need to, on the lines where the second column is 1, find the biggest number in the first column. That's the remaining part of the job. That's what the second awk does in blue. So begin, if you put begin and an awk block, this line of code only runs when awk starts up. This doesn't have a qualification, so this line of code runs once for every line of input to awk. This block of code is qualified with end. So after awk receives its last input, this line of code triggers. Okay, so this basically happens at the start. This happens on every line. This happens at the end. At the beginning, we set the variable max to 0. Then, on every line, if the value in the second column is 1, and the value in the first column is bigger than anything we've seen before, then we update the max to be the current count. And at the end, we print the current count plus 1. Why plus 1? Because if you look, if the run is length 4 of ones, that came from 5 things in the original, right? Because the runs are a thing that are between positions. And so if our convention is to count the length of the original thing, then you got to add 1 to the length of the ones. So that's what that plus 1 is for. So if we run this little block of awk code here and feed it file C and write it in file D, and do I have the braces right or something? It's like the shell's like telling me like, you're not done yet. Let's try that again. Copy and paste a little. There we go. 5, because the longest run in the original would have been 5. The length of the green thing would have been 5. So basically then this prints out the max increasing length for one simulated trial. This loop now does 1,000 trials. So what comes out? But now you see another pipeline. So this redirection treats this whole business as something producing standard output. and we take the output of that and pipe that into this. So basically what's pouring out of this red block now is numbers like 5, 7, 9, 7, 7, 7, 5, whatever. That's the simulated runs. We now need to histogram those. How can we histogram those? UNIX-C almost does the right thing, but UNIX-C only does the collapsing for lines that are the same when they're together. So the first thing we need to do is we need to sort that list that comes out into numerically increasing order so that all the 7s get grouped together next to each other, so that UNIX-C will find the 7s all at once. So we're almost there basically. So if I make something like this, right? So that's this, and I do UNIX-C on that. That's not going to group all the ones together because they're not all in this together in the file. But if I did the sort-n, the n means numeric sort. We'll talk about that in a second. Sort will group them all together. And so after that, then I can do the UNIX-C, and now I get a real histogram. The -n for sort is needed because normally sort sorts by strings. So if I make another test and I give numbers like this, and I sort that, you'll see that that's not right. Because sort as a string, if you remember how dictionary sorting works, you compare the first character and the one that's smaller is first in the dictionary. But if the characters are the same, then you go to the next position and so on. And you go to the first position that differs, and then who's left goes there. But notice that does not work for digits. Right? Because digits you're supposed to read from kind of right to left and not from left to right. And so there's a difference in sorting between sorting things in dictionary order and sorting things in numerical order, like as integers. And sort takes an option -n that activates numerical sorting rather than string sorting. And in that case, sort-n will put them into the right. So that's it. So so composing this, we're probably not ready to be there yet, but maybe you start to appreciate now the power sort of like these pipes and stuff like this. We can do a fairly sophisticated business pretty easily, and it's pretty fast to run there. I mean, that only took a few seconds to run those files. Okay, so our goal is to kind of work up to the point where these are the kinds of things that we can spit out, easily, right? Where this is just sort of natural to us to kind of build pipelines like this. And of course, there's always more than one way to do things. So like that last stage where I did this kind of awk with this running max thing or whatever, we could have done that another way too. Remember, that's the stage where we're kind of at this kind of view of the file, and we need to look at the lines that end in 1 and find the maximum of those in the first column. So another way to have done that would have been to use grep and to filter to only the lines that end in a 1. I mean, I in more questions of style. So depending on how you've seen grep, you might have seen this with a -e. You probably don't need this. We know it's going to be a space character. So you could have done something like this. It'd be about the same. It's all just kind of style differences. But here, grep is going to filter, throwing away all the lines except the lines that end in a 1. And then we have a simpler awk that just takes the number in the first column and adds 1 to it and prints it back out. Then we could sort numerically and take the last line. That would be the biggest number, right? So if we sort numerically and take the last line, that's the same thing as max. So this sort tail is basically max numerically. This awk guy is increase the number in the first column by 1. And then this grep guy is only the lines that end in a 1. And if you put that all together, it's exactly the same thing that this does. It's just a different way of doing it. And that's common too. There's always a lot of ways to do something. It's not like there's just a unique solution. Okay. So that's what we kind of want to build to, so that those kinds of things are natural. Let's see, we've kind of done all this kind of stuff already. Let me show you this one little trick I did, because you saw that I had a GUI text editor window. Maybe I already closed it. Okay, let's see if I already closed it. So I'm going to do, here is a GUI text editor window. On Mac, you've got applications, utilities text edit, or maybe it's an applications text edit, maybe it's not utilities, I don't remember. But text edit is a built-in OS text editor. On Windows, you've got Notepad. On Linux, you got a lot of options or whatever, but you need some kind of text editor of your choice. So Notepad++, it just doesn't matter. Just get yourself a text editor. Like on the on Mac, I just use plain text editor. It's fine. I use it a lot. You'll actually see that, for example, right now my one is called Untitled 993. So it's been a while since I've quit text edit. But a very powerful way of kind of getting things done is to sort of combine your terminal editor window with like a local GUI text editor. So like, suppose I've got little blobs of text here, like this, in this case, it was just this little file here, and I want to get it into a file on Hoffman. Now you've got programs like CyberDuck or FileZilla or SCP or whatever. You've got some way from Workshop 1A that you should have to be able to transfer files from your local laptop to Hoffman and back. But for little things like this, it's kind of inconvenient to drag out some of those things or whatever. So here's a way to do it. Like once you get good at it, it's like less than a second. So like, let me just clean up files again so we don't have other distractors in the way. I want to get this little blob of text on my GUI text editor window into a file on Hoffman. So, and now that we've talked about standard input and standard output, the explanation will actually make sense now. Otherwise, this is very hard to explain how this works. So I'm going to redirect, maybe I want the file to be called A, whatever. So I'm going to do cat with its output, standard output redirected to file A. But I didn't give cat a file name. And so cat will try to read standard input. Standard input is my keyboard. Okay, so I will GUI, select all, copy, terminal window, paste. We're mostly there. We just got to get out of this somehow. How do we tell cat we're done? That's a little, the details are a little tricky, but it's very simple in practice. You just type Control D. So I'm now going to type the single character Control D, and you'll notice cat has stopped, and file A is here, and it's got the right contents. All right, now that's the slow version of it. Here's the fast version of it. Once you kind of your fingers kind of get the finger memory for it. So now I'll make a file B, select all, copy, paste, Control D, done. Right, you can get it to like literally like 1 second when you're kind of used to it. And so that's a very nice way to kind of very quickly kind of get small text files up to Hoffman. Now, how do you get small files down from Hoffman? Just use your terminal window scroll back. Okay, so just do cat, get it on your screen. Just use your GUI, grab it out, copy, switch to your text edit window, paste, boom. Okay, that's a very simple download of a text file. Okay, and usually your terminal window should scroll back a way. You should be able to scroll back 1,000 or 10,000 lines or something. Sometimes it's an option in the terminal editor somewhere. How many? I think mine's probably set on this computer to 10,000 or something. That's super easy way. So like, you've got like a little shell script or something. So you just cat it out, copy, paste it over here, make your edits, copy over here, a little cat trick, and paste it again, and done. Of course, if the file already started, if you're doing many iterations of like a shell script or something, you already started it, probably editing it with a text edit window over on your GUI thing, and then you don't need to, of course, keep copying it backwards. You already know that your window already has the same copy as on Hoffman. In that case, you just keep making your edits over here and just keep pasting them over repeatedly or whatever. Anyway, so that's just a little trick to kind of, very quickly get small pieces of text in both directions, because it can be a pain to sometimes dry out one of the big file transfer things for such small jobs. Like I say, once you get into flow, you can kind of do that in like literally 1 second, and you just don't break your mental train of thought at all or whatever. Also, hopefully you figured out that there's all this kind of like command editing you can do in the shell. So like if you use the up arrow key, you'll see that you can pull back your recent commands, right? So up arrow, down arrow goes the other way. Left arrow, right arrow, you can move around, you can delete in the middle, retype, whatever, so you can edit things. If you got a command wrong, because like you mistyped, I can do up arrow, backspace over, delete that, retype that part, re-hit enter, and fix it, and so on. Some more keyboard shortcuts there's an infinite number of these, and there's just a point you just kind of learn whatever makes sense to you. Like some people really get into it, other people don't care at all. But Control A takes you to the beginning of a line. I don't know if you can see on the screen the little underline, which is where the cursor is right now, but now we're at the beginning of the line. Control E takes you to the end of a line. A is the first letter of the alphabet. E stands for end, I guess. I don't know. Control K, I think, deletes from where you are to the end. And Control U deletes from where you are to the beginning, whatever. Those are just they'll just help you be efficient sometimes. Okay. All right. While we're jogging your memory about stuff from workshop 1A, you remember how to move files around and copy files. MV is move and CP is copy, right? So if I go like into one of these directories, let's find some files. Let's maybe go into this small example. So now I'm in workshop 1B small examples in my scratch space. And we've just got some files here. If I wanted, this is some FastQ, gzip FastQ reads from a sequencing experiment. CP, I could copy that. Right, that makes a copy. So now this one is a copy of this one. You see the file sizes are the same, 67525 bytes. In fact, in a way, you sort of don't need a copy command because you've got cat. So like, if I have this file, all right, if I had done this, that's essentially a poor man's copy command, right? Cat produces on standard output a copy of the file, which we shell redirected into a new file. We made a copy of the file. So now these two files are the same, 29 bytes. They're both 29 bytes. They have the same content. But CP, copy files are going to use CP. But you now, you really understand kind of now why this works. What else? Sometimes you may wonder like why that whole dot thing, like when we're talking about path names and I said dot doesn't move you at all or whatever. Why is dot a thing then, right? Why would you ever need it? Well, the answer is that an empty string is not a valid path name. And sometimes you need to refer to the current working directory. And you can't do that. You can't say nothing. You have to say something. And the answer is that's what dot's for. So like if you want to say here, where I am now, current working directory, dot is good for that. So like, then you get rid of these guys that we just made. Back up a level. So now I'm at the top level of my scratch space in here. Let's copy something out in an interesting way. So like suppose I wanted to copy out like this W1ext.gz file, but I want to copy at my top level, right? So the relative path to that thing where I am now, my working directory is my top level. The relative path to that thing was this, right? So copy this, paste, okay? So you need to go into this directory, then this file, relative to where I am now. That's the file I want. And I want to copy it to where I am right now. So I could do this, but it's just as easier to say dot. Because that's dot means, dot is a relative path. It's relative to my current working directory. But dot means stay where you are. So if you like, that basically is how you say current working directory, the dot. And so now I've got a copy of this file right here. And the one there should still be there. So the ls, that guy, he's still there. So now we have two copies. But yeah, the dot thing is that's what dots are around for. It's a way to say current working directory. You know how to make directories? That's make dir, right? That makes a directory. Rm dir removes a directory, has to be empty. Rm is how you remove files. Okay. And rm will not remove directories. Okay. Rm dir will not remove files. Just the way it works. Okay. Yeah, you have to use rm for files and rm dir for directories. If you need to delete something very big, you can use a recursive delete, but those are very dangerous. So you got to, before you ever do one of those, you always be very, very careful. So suppose let's do like take that whole small examples directory and copy the whole thing. Maybe we'll do one with even more levels of nesting. We'll do this guy because I think this guy has multiple levels. I don't want that. Yeah. Okay. So here's here's a guy with a lot of files in several directories. So this subdirectory here, let me get it right. So let's go to the top level, and it's in the workshop 1b directory, and then it's the stage 1 style 2 directory. Okay, I'm going to pipe that to less because it's pretty long. Okay, so that's got stuff at the top level, and then it has a subdirectory called out. Oh, let's go back to the beginning. There's a lot of stuff in the top level, but then it's got a subdirectory called out, and inside out, it's got more stuff. Okay, so it's at least got 2 levels of stuff. So suppose I want to copy all of that as a whole thing to where I am now, current directory. So CP won't do it because CP just does files, but you can do dash with capital R, which means recursive. And that means everything that's a directory, go inside there, copy that stuff too. If there's a directory in there, keep going through the entire directory tree. So this dot is the destination. And so it'll copy that whole thing recursively. Usually in this case, I would add a few more options. P preserves permissions, things like the last modified time, the group owner, the RWX bits, the P preserves all that. V is verbose. That'll give us a line of progress information. Every time CP copies a file for big copies, you're going to want to kind of know what progress it's at, and the V does that. And the I stands for interactive, and what that means is that if one of the source files already exists at the destination, it would warn you before overriding the destination. So it's a safety feature. So usually I would do kind of a big copy PRVI is the usual, I would say. And so we'll do that, and you'll see it's copying all those files. Now it's in the out subdirectory, and it's going inside there and copying inside there too. And you see kind of the progress information. It's source, arrow, destination. So I think there's 21 parts, so it's almost there we go. So now we see we have a copy at our top level like this. And if we look inside there, it's got all those files, and inside out, it's got all those files. Now, how would you delete all of that, right? You don't want to have to do RM and give every single file individually. You do know from workshop 1A things like the star pattern and stuff. So like if I do echo A star, you'll see that the shell expands that into all the matching files. So I could do RM A star, and at least that would get rid of all those. Maybe I'll do that just so you can see. Yeah, so that'll kind of kill all those. The list is much shorter here now, but there's more files to do. With the star pattern, it wouldn't be that hard to clean this up. But for really big things, there's a recursive delete too. So RM, the option is little r for recursive, and that's going to blow away the whole thing. But be real careful with these RM-Rs, because like suppose you pointed that at your home directory, you're going to have a bad day. Suppose you point that at your project directory, you're going to have a bad day. It's going to delete everything, and it's not going to ask, and it's going to do it fast, and there's no, and it's hopefully you have a backup. So yeah, and then before I do the recursive delete, let me show you one more thing about RM. If the file doesn't have write permissions, so like you see, I took away the W bit from this file, RM will ask about those. So if I try to RM, you'll see it says remove write protected regular empty file. Well, it's an empty file, but the main thing is that RM calls it write protected. It means it doesn't have the W bit. It knows the ones without the W bit. You probably intentionally made that way. And this is like a little like, are you sure kind of thing. You won't get are you sure on regular files. So if I make one with the W bit, RM will just blow us away with that one. But the ones without a W bit, it will ask you for, and if you say N, it won't do it. If you say Y, it will do it. When you have big directories, some of the files inside might be without the write bits. And in that case, usually you combine the R with an F, and the F means force. And that means don't ask. Just even if it's got no W bit, just do it. So these RM-RFs, it's gone. Whatever. I could have added a V to get the progress information, and you'd see each file is deleted. But yeah, be very careful with those RM-RS. For places that are backed up, Hoffman does have super secret backup directories. They don't show up in listings. So your home directory and your project paid storage, actually, you do have kind of a way out if you accidentally delete stuff. So if I look at home C Cocos, like my home directory, you can look at yours. You'll see you don't see a directory called snapshot in here, right? You don't see a listing. It's not in the listing. There's sort of some magic there. But there's a super secret directory in every place, in every directory on one of the backed up file systems called .snapshot. And you'll see that there's some in there. There's weekly backups for 2 weeks, hourly backups for the last few hours. This is probably 15:05, that's 3:05 p.m. It's 3:51 p.m. right now, so it goes back to 10:05 a.m. today. 2 dailies, 2 weeklies, and a bunch of hourlies. And if you go into one of those, like the most recent one would be what? That'd be like this 15:05 hourly. Or maybe you got to go back further because maybe you did the delete a week ago and you forgot. So we'll go back 2 weeks. April 7th. That's the oldest one. That is what my home directory looked like on April 7th. And maybe you deleted something in here, like maybe this pipe viewer directory you had deleted or something. So I could copy CPP or VI that out to my scratch space. So and now in my scratch space, I pulled out from the dead a copy of the thing I deleted. But you really don't want to rely on that kind of stuff. But yeah, just be careful. If you're lucky and the timing works out right, you may be able to pull stuff back out of your home directory, your project directory. Scratch, it's just gone. So be real careful with these like RM commands, like these recursive RMs and stuff. Okay, we've actually talked about this slide already. I wouldn't worry about NanoVim and Emacs. You just can use your GUI text editor and file transfer back and forth to edit your files on Hoffman. You don't really have to know that. Let's see. Yeah, okay. All right, we might as well do this slide now, and then we're close to just kind of switching topics and doing something else. Okay. All right. One way to transfer files, like I said, I don't know what file transfer software you guys are using, but if you're using the SSH command, so like for me, the way I got on Hoffman was SSH, focus on Hoffman to edu. This is the open SSH command. The SSH command in OpenSSH has a companion command called SCP. And just like I have passwordless login to Hoffman, my SCP will also be passwordless. And this makes transferring files very kind of convenient. So let me show you how kind of the command line world does file transfer. So you have to decide what local directory you want to transfer to. So the easiest way to get that settled is to change your local shell's working directory to the place you want. So common places would be, so one of the things the shell does is the tilde expands to your home directory. So on my Mac, tilde expands to users cocus. Let me get another window going. On Hoffman, tilde expands to, if you do it right, echo tilde, u home c cocus, because that's my home directory on Hoffman. But on my local machine, it's users cocus. So if you want to switch to your home directory, you can either just do CD, like we haven't shown on Hoffman yet either. But if my current working directory is in my scratch, and then I just type CD without anything, it takes me back to my home directory. You could also do CD tilde. That's the same thing. The shell will expand the tilde to your home directory, and then the CD will change to that. It's all the same. Same thing on my local machine. It's just that their directory is different. It's users cocus instead. So CD puts me in my home directory. On most GUIs, like my desktop, like here's my desktop back here. Your desktop is in a directory called desktop with a capital D in your home directory. That's true on Mac. It's true on Linux. It's almost true on Windows. It used to be true on Windows for a long time. And then Microsoft OneDrive came around. And at some point, I don't know if it was Windows 10 or 11, but they started forcing like everybody onto OneDrive, even if like you didn't want to be. And probably these days, unless you took in like real steps, if you're on a Windows machine, your desktop GUI directory is probably a subdirectory of the OneDrive directory, which is a subdirectory of your home directory. So in that case, it's like home directory OneDrive desktop instead of just home directory desktop. But it's sort of not a big deal and doesn't matter at all if you're not on Windows. So anyway, decide where you want to put stuff. So like maybe I want to put stuff on my GUI desktop. So I will change to my GUI desktop. Okay, I'm on my local machine here. This window is my local machine. This window is Hoffman. So here's all the stuff on my GUI desktop on my local machine. And maybe I want to transfer a file to Hoffman. Let's push a file to Hoffman first. So what file do I want to send? Well, maybe I've got like, this is one of my collaborators, and there's a directory here, and it's got some files, and I want to transfer up to Hoffman, maybe like this file and this file, say. So it's like the Todd star.gzs or something, right? Actually, this is a GZ, but it's not Todd GZ. I think the Todd GZs are these two, right? So in fact, if I did Todd/Todd_star.gz, that's probably exactly the files I'm transferring. Nope, it's got that's 4 files. All right, so maybe I got to add a little more. So if I do Todd TM-mummer star, that's the 2 files I want to transfer instead. Okay, so I've got my little shell pattern worked out for what the files I want to transfer are. So then all I do is I say SCP, and we'll do this PR thing in a second, and I'll tell you why that's there, but basically it's source destination. So the source is this, and the source can have patterns in it, shell patterns, no problem. The shell will expand those out to those 2 file names. And now I got to say where I want it, the destination. The destination is done by using your Hoffman username, and then the Hoffman machine, : and now you put the path on Hoffman where you want to put it. So maybe I want to put it in the top level of my Scratch space, Scratch C code. And I'm going to hit enter, and you'll see that SCP does the transfer, pushes it up. And now if I look in Hoffman in my Scratch space, there it is. Those 2. So that's kind of cool because you've got the shell patterns to do it, but it's even kind of cooler because I didn't have to type a password. And in fact, this is just another command line command, and it could have shown up in a shell script or anything like whatever. Like this is automatable, right? So like, whereas like GUI clicky stuff, like you can't really automate. This is just sort of like lives in the same command line world everything else does. And sort of this becomes something that you can kind of automate and include in scripts and stuff, file transfers. That's the reason why I'm kind of showing you this right now. Not that we really have shell scripts yet and so on, but the point is of the command line file transfer world is that it kind of puts everything back into the same world rather than kind of escaping off the GUI world. And so, kind of, because once you kind of get really into command line, you want to do everything in command line. And the second reason is because, yeah, you get the shell patterns as a bonus there. I usually do SCP with P and R for the same reasons that I do CP with P and R. The P means preserve permissions, so that keeps the modified dates the same and stuff like that. And the R means recursive. So if the source here was a directory tree full of all kinds of stuff, the SCP would have done the copy of the entire tree and not just the top level or something. So that's pushing up to Hoffman. How would you pull down the other direction? So here is a directory in my Scratch space that maybe I want to pull down. So let's just see what's inside that directory. So this is my Scratch directory, the Workshop 6, Day 3, Stage 9B Deep Tools. So there's a bunch of stuff in here. And maybe I want to download just the PDF files. These are Adobe PDF reports that a pipeline made, and I want to visualize them on my local machine. I have a PDF viewer on my local machine, so I want to copy the PDFs of this thing down to me. So the pattern the shell pattern that I want to download from Hoffman is this star.pdf in this directory. It's these files here that I want to download. So how can I do that? So I can do SCP. I might as well do the PR. I just kind of always do that, and generally doesn't hurt even when not needed. So now we got to reverse the order. Now we got to do the Hoffman side is the from, and the local side is the to. So where do I want to copy from? This place. And this is the pattern that I want on Hoffman. Okay, so I'll put that there. And then where do I want it? I'm currently sitting on my GUI desktop as my local working directory. That's fine. I'll put it there, dot. That's okay. But this isn't going to work. And I'll show you it not working first. And oh gosh, this works, but for really stupid reasons. Okay. Yeah, okay. If you can get away with it, that works. But the safer way is that we actually needed the star to expand on the Hoffman side and not the local side. My local shell actually tried to expand the star thing, and it didn't work because this whole thing is not a place on my local machine. And so then you need to know the rules are, what does the shell do when you have a file name pattern that doesn't match anything? And the answer in that case is the shell leaves the whole thing alone. So if I, am in a place on Hoffman, say, and I do a pattern star.txt, there are no txt files in this place. But you'll see that what happens is then, in that case, the shell just leaves the pattern alone. So even though I didn't escape this star, where are we here? This star, even though I didn't escape the star from my local shell tried to expand and it failed, and so left it alone. That means when SCP transmitted this to the other side's shell got this as an asterisk and did the expansion on the remote side. Like that's exactly what we wanted, and we did copy the files we wanted, and they're sitting here on my desktop, and I can look at them with a PDF viewer and whatever, and they're here. Everything's great. Probably we should have just escaped this asterisk from our local shell, because that's really what we wanted to happen, and it's only sort of through the accidental rules of shell that say if a pattern doesn't match, you leave it alone, including leaving the stars in place and stuff. So the point is just to get these shell patterns to expand on the other side and not on our side, right? So that's what that's about. Anyway. Okay. And one last file transfer thing, and then maybe we'll take another break, and then we'll be on to different topics. We have these sort of random things to kind of cover. So unfortunately, due to the, I mean, it comes down to like this first slide, right? With these teletypes, all right? These old teletypewriter machines, they had to make the paper go to the next line, you had two things you had to do. There was a little mechanical device that printed the letters, and then there was the paper mover mechanism. So when you start typing letters on the thing, and then you need to go to the next line, two things need to happen. The paper needs to go up, and the little printy thing needs to go to the left. So this is called line feed, and this is called carriage return. So to go to the next line, you need to do carriage return and line feed. And so in the old days, the computer talking to the teletype would have to send two characters at the end of every line. Didn't matter what order you sent them in, because carriage return line feed or line feed carriage return have the same end effect. It sort of mattered because one of those was slower than the other, and it doesn't matter. Anyway, so then when glass TTYs came about, you didn't really need both things anymore, because like it's not a mechanical device anymore. Now you could just say like carriage return would need both things, or line feed would need both things. And the problem is in the 80s, then sort of like operating systems kind of exploded, and everybody kind of like chose what to do. And the answer is that some operating systems chose what's the slide we were just at here. Some operating systems chose just carriage return. Some operating systems chose just line feed. Some chose the two character sequence carriage return line feed, and some chose the other way around, line feed carriage return. Current Mac OS, Unix, and Linux all do line feed only for the ending of a text file line. Windows, unfortunately, chose carriage return line. And what that means is that if you're not on Windows, everything's great. But if you're on Windows, text files on your local machine do not have the same line endings as text files on the other side. And that causes endless pain, because it means when you transfer files between the two sides, the line endings need to be translated. The next complication is that it's not always clear to a file transfer program what files need translation and what don't. It can't just like translate them all, because like binary files get destroyed if you try to translate them. If you accidentally try to change line endings in the binary file where the characters 10 and 13 don't mean line endings, you will destroy the file. So to be on the safe side, file transfer programs have to not translate. So they kind of maybe look at the file. If it looks like text, they might activate translation or something, or maybe just they never translate because that's safer or whatever. So this is a pain, because some Unix programs tolerate the Windows line endings and some don't. Generally, Unix programs will never generate Windows line endings on their own, but it means you end up with files that can be living on Unix that have the wrong line endings, and some programs work and some don't, and whatever. Let me show you what it kind of looks like, just so that you see the effect. Is anybody on Windows here, or you're on Windows? Okay, all right. So, yeah. So here in like the workshop 1B directory, in the small examples directory, I've got this workshop one example, Windows line endings.txt. So if I look at that file and just cat it, it'll look okay. Okay. It's 10,000 lines, which consists of an integer and a short sequence, a DNA sequence. However, if I use the right kind of tools to look at them, like here, I'll use vi-b just to show you, but there's kind of this extra character at the end of every line. This control M is the Windows. Windows uses carriage return line feed. The line feed is the one Unix pays attention to. So if you take a Windows file and look at it on Linux, the CR looks like an extra character at the end of a line, because this LF is going to be treated as the real line ending. The CR comes before. CR is 13 in ASCII. 13 is the 13th letter of the alphabet is M. Control M. That's why you see the control M's at the end of every line. That's the Windows. That's what Windows line endings look like on Unix. But some things don't care. When I just added the file, everything looks okay, because my terminal emulator, when you print out a line and you start printing like 9978-whatever, the terminal emulator is printing this, and then the terminal emulator is right here. And then the Windows file says carriage return. My terminal emulator then goes back to the same line on the screen, no problem. Then it gets the line feed, and now it moves down to the next line. So you can't see it, but it really actually simulated exactly what an ancient teletypewriter would have done, right? It moved the carriage check to the beginning of the line, and if you then printed more characters, they would have overprinted on the same line. But then the next character says go to the next line. So that happens so fast you don't see it. So you don't see the effect in this catting of the file. But some programs aren't going to be happy because they're going to expect, say, a DNA sequence, but they're really getting DNA sequence and a control character. It's going to mess them up. So the problem is sometimes it's hard to see them at all. Like I say, if you're just catting the file or whatever, you may not even know that you have the problem. You generally have to use some program that shows you like the funny characters in a file to see it. So like VI editor in binary mode could do it. You could hex dump the file and see the actual bytes of the file. So like if I hex dump this thing and look at it, this is the actual bytes of the file. This is the hexadecimal codes for successive bytes. This is the characters as characters. But what you can see here is like this is one tab and then this DNA sequence. But this is where the line endings are, right here. This 5454 is the TT, but then you see ODOA. In hex, that's 1310, carriage return line feed. So we know this is a Windows line ending thing. I'm not saying it's easy for you to detect when this happens or not, but Hoffman makes it easy to convert the files if you happen to kind of either be worried about it or you know that it's a problem. So if I say DOS to Unix and I give it the name of this file, it'll rewrite the file in place, translating the line endings. So now, if you notice, the file got a little shorter. So it was 148,894 bytes. Now it's 138,894. 148, 138. It shrunk. It shrunk by exactly 1,000 or 10,000 because there's 10,000 lines in this file, and each line needed exactly one character deleted, the extra CR. So the file size went down by exactly 10,000 characters. And now if I use any of my methods like the vi-b, you'll see it's clean. Or if I use my hex dump, you'll see that the line endings are now, here's the line ending, that 54 is the capital T, this 32 is the 2, and between there's just an OA anymore, which is 10, which is the line feed. It's correct. And to go backwards, you can go Unix to DOS, and you can give it a text file, and it rewrites it in place, and it puts it back in Windows line endings. So it's stupid. We're still dealing with this in like 2024 from this. It's really a side effect of the 60s. And it's just, I don't think we're ever going to escape. The Starship Enterprise has line ending problems on it, in the year 2400. I mean, it's just ridiculous. We're still dealing with this. But like I say, it's kind of a nasty problem because like you don't even always realize it's happening, and some of your software will just act weird, and it may be this reason and stuff. So just know if you're coming from Windows, depending on your file transfer software, maybe it made an attempt to translate text files, maybe it didn't, whatever. Maybe your software on Linux is sensitive or not. A further complication is that if you have compressed files like gzip files or zip files, file transfer doesn't usually see inside those, and those are binary files. So if you have on Windows text files, you zip them up into a zip file, you move them to Unix, and you expand the zip file. you're going to have files with line endings, with Windows line endings there, because the file transfer just saw a binary zip file. It didn't know that it's supposed to uncompress the zip file, translate all the text files, rezip the file. I mean, that's crazy to ask for a file transfer software. So yeah, it's kind of a problem, but anyway, sorry if you're on Windows. It's just a fact of life. We can't go back in time. You know, if you have one chance to go back in time, so many decisions. One of them would be to take Bill Gates and to, you know, you're not doing character tune line feed. You're doing line feed. That would have made the world a lot simpler. But such as it is. Okay, did we take our second break yet? No, I think. So let's take another 5-minute break, and then we'll move on to different topics. If we just push through, nobody wants to take a break. No? Okay, so back in, you know, from what workshop 1A told you, and from this slide, actually we're supposed to not use the login nodes to really do anything, right? We've actually just doing everything today on the login nodes, and it's kind of okay because we haven't really done anything serious on the login nodes. The login nodes you don't really want to do real work on because they're a shared resource, right? Let's look at one of these login nodes. I'm on login 1 right now. So if I use the W command, that'll show me everybody logged in to this machine right now. And if you see, it's quite a few people, right? Well, we could pipe it to WC, and it's about 120 people. There's probably like this line at the top, or 2 lines at the top that are header lines. So it's 118 people on login 1 right now. And that means we're all fighting for login 1's CPU time, network connection, and access to Hoffman's storage IO. And it's okay because it's a fairly, you know, fast machine and whatnot. But if all of us start trying to do massive file copies at the same time, or if we actually start trying to run real analysis pipelines on at the same time or whatever, that machine's quickly going to bog down. And because the login machines are the only way to get from the outside into Hoffman, everybody will suffer, right? There's only 4 of them, right? So that's why you don't do anything serious on the login nodes, because they're the bottleneck that we're all going through as a shared resource. So one of the first thing, basically, every time you sign into Hoffman, you should do is switch from using the login node to getting a session on an interactive session, at least on one of the work nodes, the main pool of the cluster, the 800 nodes that really form the cluster, and just use the login nodes as sort of a network relay for you, where, you know, we have to SSH into something, we SSH into a login node, then we're essentially going to SSH into a work node, and then the middle machine, the login node, is just going to act as a network forwarding point that just forwards our keyboard traffic down to this guy and takes the output, screen output from this guy, and forwards it back to us. It just acts as sort of an extension cable for our virtual serial cable. And so that's this. We should be on a compute node. So you should have seen the QRSH command. And this is going to be important because when we start doing jobs, they're going to look very similar to this command. Most of the mess of this QRSH command is specifying the resource requirements that we want to use. Now, maybe in workshop 1A, you just did QRSH with no arguments. And then in that case, a lot of defaults happen. But basically, QRSH is your first interaction with the Hoffman job queue and scheduler. And the way the scheduler works is that, you know, the scheduler has this pool of 800 machines. And we haven't talked about the job queue yet and so on. But if I do QStat, which will show me the current contents of all jobs running and waiting on Hoffman, that went by really fast. Let me quite get to less that you can see it. There's the top of the list, and I'm going to just hit spacebar a bunch of times, and you can see this list is pretty long. In fact, if I do QStat WC-L, there's like 7,000 entries in this queue. So the queue system is staring at sort of this massive scheduling problem it's got 7,000 jobs that it has to deal with right now. Some of them need multiple nodes and different resources. Some of them need a lot of RAM, some of them need a lot of CPU, whatever. And then it's got this pool of 800 machines, which vary in how much RAM each machine has and how many CPU cores each machine has. And these jobs each have time requirements on them. Like this job is set for 4 hours, this job's set for 23 hours, this job's set for 3 days. And the scheduler has to try to match it all up, right? It has to try to figure out how to plug jobs into these nodes so that everybody, as much of the cluster is in use at any one moment, but also be fair so that people that submitted huge numbers of things aren't monopolizing the whole thing and so on. Very complicated how priorities and the scheduling things match, and maybe you can appreciate the scheduler's got a tough job. So when we do QRSH and we want to get a work node, the scheduler really needs to know some things. It's like how many CPU cores you're looking for, how much RAM you're looking for, and how long are you wanting this, right? Because it has to figure out a hole in the schedule to place you. If you just do QRSH, there's going to be some defaults. I'm not quite sure what they are. I think they've changed over time. They're probably pretty small. It could be like 1 core, 1 gig of RAM or something. Almost always you should explicitly specify kind of how much resources you want. Now it's a complicated question because that depends on what you're going to run inside there. And figuring out how much resources a given set of commands runs and so on is complicated. So, the danger is that if you ask for too little, things are going to break. Like you ask for too little RAM or something, programs just crash and stuff. If you ask for too little time, then your program just gets aborted in the middle because the scheduler will hard kill you. If you ask for 3 hours and the clock says 3 hours, that's it. Scheduler kills everything running, and that, whatever, probably you lose everything because a lot of programs don't write their output to the end. So that's the danger. You always kind of want to round your resources up because things work better for you that way, right? Things don't crash, programs finish, and so on. The danger is you don't want to round up too far because if you ask for too much resources, the scheduler won't be able to find a hole for you, or you'll wait a long time to find a hole, right? So if you ask for 7 days, 256 gig of RAM, 64 cores, you're going to wait forever, basically. There's probably a few machines in the cluster that could satisfy that request, but the scheduler is going to have to empty everything out of those machines to be able to satisfy that request. And so some of those jobs may be running for the next few days. The scheduler will carefully try to clear off that machine for you, but like I say, you're going to be waiting maybe 3 days for that request to be satisfied. So yeah, so getting things, waiting not much time means you want to have your resource requirements low. Having things work means you want to have them big. And it's just kind of like you got to find a balance, and it's all just kind of a delicate thing depending on what you do. We'll talk a little bit more about that when we actually start running some job queue jobs for real work. So basically what that means is that kind of at the beginning, you just kind of choose some numbers kind of that are reasonable and relatively easy to be satisfied, but still pretty big and useful to do a lot of things in. So that's what I'm showing here. So here I'm showing a request for 5 CPU cores for 3.5 hours with 4 gig of RAM per core, and 4 times 5 is 20. So it's 20 gig of RAM total. So this is a moderate size request. You could go smaller. You could go 3 cores or even 1, or reduce the memory a little bit. But like I say, the memory on average in the cluster is like 5 gig of RAM per core. So you really kind of like this number and these numbers kind of scale together because it's kind of like that makes sense. So if you run one of these, like with these requirements, hopefully you don't have to wait too long. Right? So I just pasted that in here. We'll see how long I have to wait for 5 cores, 3.5 hours, 20 gig of RAM. And it's not instant, that's for sure. I'm waiting. It's not like it happened in 5 seconds. And I did this yesterday. Oh, that wasn't too bad. I've got one now. So node 6008 replaced me up. You may have to wait longer. Some of this depends upon whether your PI has contributed hardware to Hoffman, because Hoffman has hardware, like some of the hardware comes from I don't know what pot of money it comes from, but it's either the university or one of the kind of higher level things. Other hardware is actually contributed by departments or individual PIs. Like your PI can buy in to Hoffman and contribute nodes and stuff. If you buy in, you kind of get some perks and stuff. So like your priorities kind of improve, and like you're allowed to request high resources on the nodes that you bought and stuff, and so on. But anybody on campus can get a Hoffman account. It's just that if you come in as a general campus user with no other affiliation, you're going to be at the bottom level of what Hoffman gives you, right? And you're kind of going to be waiting the longest and have the smallest kind of resources available, which are still quite a considerable amount of resources. It's just like, I'm just saying, it just varies. So like, how long you're going to wait for a given resource request is going to depend on how loaded the system is that moment, what your affiliation with Hoffman is, and so on. So I didn't have to wait very long. Hopefully you wouldn't have to wait very long. Did you guys try with this particular line? Did you get a session yet, or you got a session? Didn't have to wait too long. No, okay, that's good. If you are waiting a long time, you can hit Control-C and maybe reduce these numbers. Like maybe try this as a 3 instead of 5. Maybe reduce this to a 3 and then multiply this out. If this is 5 and you chose 3 here, then you put 15 here and stuff. Just try to find a level. Nothing that we do in this workshop, I think, needs really a lot of resources. But just for your own purposes, you should probably try to find a set of numbers that kind of reliably over days works for you. Like, what's a good set of numbers for you personally that you find that like you can get a session relatively fast, and then that just becomes the default that you request when you start each day. To kind of get you ready for some of the scripting that we do, why don't we introduce some shell variables? We might have seen a few already. I can't remember here, but one thing that's commonly you're going to do. So eventually we're going to have like these kinds of commands inside scripts and stuff. And in that case, one of the things that's kind of annoying here is that like this number is equal to this number times this number. And it'd be kind of nice if like that was automatically enforced for us, instead of like every time we change the script or something, it's like we'd have to remember to keep these in sync. And also it's kind of like maybe hard to remember what some of these things mean, right? So like, what is, maybe if you've been away for a few months and it's like, what is this PE shared 5 is? What's the 5? So one way to kind of get around these things, I mean, this is like the application we're showing right here isn't really a big deal because it's like a lot of complication for not much benefit right now. But this sort of idea here of like documentation and keeping things consistent when making changes motivates this here and is important later on once we do more scripting. But like, here's how shell variables work. So in the shell, you can just name a variable anything and assign it to any value. So this is a shell variable called capital ABC. Its value is DEF. The only reason why you have shell variables is to use them at some point, right? And you use them by expanding them back into their current values. So if I ask what's the current value of ABC, it's DEF. The way that works is echo is a command just like it always was. It's just that the shell first translates, the shell that takes this argument. Echo does not see this thing with $ and braces. The shell is looking up the value of this variable and then replacing it with the value it currently has. And echo only saw the expansion. So the shell recognizes this magic sequence as something it should expand, looks up the current value of the variable and plugs it in. Okay. If I change the variable to be something else, and then rerun the same command, of course, the expansion is different because the expansion, the value of the variable is different. So that, in a way, that's almost all there is to variables. You can set them and you can get their value. Of course, there's a lot. You can do more complicated things than stuff, but it boils down to essentially that all the time. So one way you use those is to just use those instead of having magic numbers floating around. You just give them names that make sense. So like this 5 is really the number of CPU cores. So we could put that in a variable that just identifies that. The number of CPU cores is 5. The gigabytes of RAM per core I want is 4. The runtime that I want is 3.5 hours. And then in the QRSH command, I just use those variables instead. So like I say, this indirection isn't really helping us here, but it does have some benefit for the documentation effect. But once we get into scripts in more complicated situations, you'll appreciate this a little more. But basically here, I've just sort of used the variables instead of what used to be the raw numbers inside of here. But then I can also take care of that problem where this number is supposed to be the product of the number of cores and the gigabytes of RAM per core by letting the shell do the arithmetic for me. So I kind of showed you the shell can do arithmetic. That's with this $ double parens business. Okay, and it kind of does like what you expect, 3 times 4, 9 minus 11 is minus 2, and so on. Arithmetic, like you think, works in there. But one of the things you can put inside there in those double parens is shell variables, and it will use the current values of those variables. So if A is 3 and B is 7, and then I do A times B, I get 21. So rather than having just this hard-coded 20 in here, I can just say what I really mean, which is number of cores times gigabytes per core. That is the number that I want here. That's the 20 in this case. So when you have commands like this, and like when you're doing complicated shell stuff and you're kind of not sure yet whether like it's working the way you expect, just throw an echo on the front, because that won't run the command. It'll just show you what all the expansions are, right? So if you're wondering, how does the shell treat this command line? What is it transforming it into before it decides to actually run it? Just throw an echo on the front. So here is this, here, let's set the variables. So copy this here, paste it in. So those variables are now set. So like they all have the values that we just set them to. Okay. Then I can take my two-liner here, and I've got the echo on front. So I'm not worried about running it yet. I just want to see what it looks like. And here you see what the shell is doing. I guess I opened a new window and my font got smaller again. So maybe I should make this bigger. Should have done that a while ago. Okay, so here is the expansion. And you see the expansion is just the command that we just gave, literally with the numbers hard-coded in there, right? So this numcores is turning to just a 5. The run times got plugged in. The 4 is here, but our arithmetic turned into what we wanted, the 20. So the advantage of this is if I was now in a script or something, and near the top of the script were these variables, now I can change these numbers or whatever, and not worry about later on like keeping this number consistent, because the script just will adapt automatically and stuff. So like I say, this isn't too complicated a situation yet, but yeah, once we get more complicated, then that's an important feature that shell variables let you do, is they let you parameterize code. So instead of embedding all the details into the code, you can sort of like use shell variables for all the parts that vary. And then that's going to be the way that we're able to repetitively use a piece of code over and over without giving the same thing over and over again and making the edits. So like if we've got some pipeline that's doing stuff, but like the file names change and we need to run that pipeline a bunch of times with different file names, replace the file names with shell variables, then we're going to have to talk about shell functions or shell scripts. But then we're going to be able to package that little blob of code up with its variables in a way that we can call that code repeatedly, plugging in different values for the variables. But we don't have to repeat all the code that doesn't change, right? We're just going to be able to tell it the part that does change, like the file names. Like do it for these file names, do it for these file names, do it for these file names. Not like copy the whole blob, edit in the file names, copy the whole blob, edit the file names, and so on. So that's going to, shell variables are really critical to solving the repetitive problem, automating things, and so on. So yeah, we'll use them a lot more tomorrow and day 3. Yeah, question. Very good question. Yeah, like what's the persistence of these things? If I log out and log in, my variable is still there and so on. So the answer is no. It's just part of that particular running instance of the shell. So like remember how like right now my working directory is this place, right? Like if I start a new window and I sign into Hoffman again, my working directory is back to my default home directory. That's not a permanent thing. The working directory is a property of a Unix program. This particular copy of the shell on this particular computer right now. This shell is a different shell. And I think this is a different machine too, login 3, and this is login 1. So each time it's fresh. Same thing with the shell variables. Every time a new shell starts up, no variables. So yeah, they don't persist at all. The only case where you would get variables, like if you do subshells, like if the shell starts another shell, that subshell usually has the same variables that the current shell has. But independent, like each separate login, or like if I QRSH to a machine, that's a fresh login, it's sort of on that work machine. They're all independent. They don't. If you have variables, you have to set them fresh. Same thing with the current working directory. When we get to like the module system and we use like SAM tools, module load and stuff like that, all that stuff has to be done every time a new session starts, including jobs counting new sessions. we have to set up all the environment, CD, module loads, shell variables, set them all up every time. Yeah. Yeah, no persistence on shell variables. We haven't talked about control C yet. So sometimes if things are stuck, like here's the command sleep, it just waits for like sleep 3, waits for 3 seconds. Sleep 600, that would wait for 10 minutes. I don't want to wait for 10 minutes. Like, get me out of this. The way you get out of something, if you want to kill a program that's running, control C. And that stops it right away. Let's see. Okay. I think I lost my session, right? I signed out of my thing here. So I have my command here. I'm just going to remove the echo. So now it's actually going to run. Because I'm back on a login though. I lost I did get a session a while ago. You know, there it was 6008 or whatever, but we closed it. So let me get a session again. So QRSH is really a combination of Q sub, which we haven't talked about yet, and SSH. It's essentially like a cluster aware SSH. It's an SSH, but where you didn't specify the machine you're connecting to. You're letting the cluster's queue scheduler figure out what machine to connect to. But effectively, it is an SSH underneath. Okay, now I'm on node 7144. So like if you do host name, that'll tell you what host you're on. It's actually part of your shell prompt as well. Because once you start like switching machines, like you got multiple windows open and some of them are on different nodes and stuff, that's why your prompt includes some of this information. This says you are currently user focus on node 7144, just as a little bit of like context so that you like, once you get multiple windows open, you kind of keep track of where you are. This is your current working directory. The tilde means home directory. So like you probably see that as we move around, you'll see that because if it put the whole path here, it would be too long. I think it only gives you the last component of the path name. So like my current work directory, do scratch C cocus, that cocus here is this cocus here, whereas this cocus is my username. So if I switch into another, we've switched directories around a bunch of time here, but see now I switch into this workshop 1B directory. So my current work directory is this. Well, that's why this now becomes part of the shell prompt here, whatever. Shell prompts are completely configurable. We won't talk about it, but I think it's the PS1 variable. And these magic escapes are controlling it. It's username at host name, last component of working directory, $. If you really get excited about shell, you can change your prompting to whatever you like. You'll have to Google how to do that, but it's not magic. But most people live with the default. It's just fine. But that's what the prompt is telling you is your username, what machine you're on, the last component of your working directory, just to kind of give you some context when you've got multiple windows open and stuff. If you want to close a shell, you can say exit. That's a shell command to the shell that tells the shell as a program, quit yourself. When that happens, the QRSH, which is really an SSH, realizes that the shell it started died, and then the QRSH dies. And so we will be back, when I say exit here, that's an exit to the shell on node 7144. My QRSH dies, and now I'm back to my shell on login 1. My shell on login 1 has been here the whole time. The QRSH command here has been running the whole time. My shell on login 1 has been waiting to give a new prompt only after the QRSH finishes, right? So that's the chain of events, right? We're on login 1 shell, we got a prompt, we typed the Q sub command. That shell on login 1 started up the QRSH program. The QRSH program talked to the job queue, got us an SSH session to node 7144, and started a shell for us there. Everything here in this chain is now waiting until this shell finishes. We are now, our standard input and standard output to this shell is the same as the standard input and output to this shell back here, which is our screen and keyboard. So this is why our screen and keyboard is now flowing along this chain, and we're talking to this shell on 7144. Eventually we type exit down here. The 7144 shell dies. QRSH gets notified that the shell it started dies. QRSH dies. Then the shell on login 1 realizes that the QRSH command is done, and it's time to give you a prompt for the next command you want to give to the shell on login 1. That's the whole life cycle that we just did with the QRSH. Okay. And that's just a question of where we want to end up. I think we'll get to regular expressions, and then we'll kind of, day two will be sort of our working towards getting fancier pipelines in real applications going. So we already saw grep once or twice today. Let's talk about that a little more explicitly and remind yourselves about regular expressions. Oh, I keep exiting my session. So I got to get another one again. But from now on, always just first thing you do on start of every day is connect SSH to a login node, immediately QRSH to a work node, right? That's just the habit you get into. And so when you come in tomorrow, start by open up your laptop, SSH to login node, QRSH to compute node. Okay, I'm on node 6014. Okay. Let's go into this directory. Okay, here it's in my Scratch directory. You can go there too. It's readable by everybody. And this is something from workshop 6. That's our bisulfite workshop. I kept these around because I wanted you to see sort of some real data, and I didn't want to make like really kind of just like abstract, like fake simple stuff. You know, these are BAM files from real alignments, bisulfite alignments from a real experiment and stuff. And we don't care about the details right now, but it's just, we just want some real data around so we see something slightly more realistic. So one of the things that once you start running lots of jobs at a time is you have to start kind of keeping track of what jobs like succeeded and like statistics about each job and stuff. So like one of the numbers after you do an alignment that you're probably interested in is like the fraction of reads that align, right? One of the most important numbers about an experiment, right? Like, if the alignment rate is like 80-90%, that's okay, I guess. But if your alignment rate is like 20%, then something went wrong, right? Like it's the wrong genome, or the reads aren't right, or something failed, right? So you need to identify which samples that failures or something. So one of the ways that you keep track of that is to like keep log files of the outputs of programs and stuff. So like these alignments are computed by a program called VS-Bolt, and it produces output as it runs. And one of the things that produces that output is some, so let's look at one of these standard out files. This is a log of the standard output of VS-Bolt as it ran. And what you're looking at here are 1, 2, 3, 4, 5, 6 samples. These are the sample names are here. These are NCBI SRX or session IDs here to real experiments. So if we look at one of these standard out files, what we're seeing is log output from the aligner program. And at the end here, you see lines like mappability, 98% or whatever. So that's actually a statistic that the aligner produced. And maybe this is one of the numbers we're interested in, but we'd like to see it sort of like for all of our samples and stuff. So like grep is a perfect way to do that. We see that the line that identifies the number that has what line is called like mappability. So I could just grep for that word, grep mappability across all the files that I want to look at. Those standard star.standard out, right? So, and you see that's very nice. That grep looks at each file, finds the line that matches mappability, or all the lines match mappability, all 0 or more of them, and prints them all out for us. When grep has multiple file names given as an argument, grep also prepends each matching line with the file name that had the match and a colon. And it also knows some terminal magic to color the various bits. So this is the file that had the match, and this is the line that matched. And so what we can see here is we see all 6 samples, and we actually kind of nicely see the mappability line. We could have done, we could have used less or something and looked at each of these and dug them out and kind of wrote them down or something. But, if you had hundreds of samples, which is easy to do, this is a much nicer way of seeing the results or whatever, right? And so that's like a perfect application of grep to do stuff like this. So remember how that works. The shell is the one that took that star.standard out and expanded that to a list of file names. So what grep actually saw was 7 arguments, right? It saw the first argument was mappability, that's the pattern to search for, and then arguments 2 to 7 were the file names to search, and that's these. The shell is the one that expanded that pattern into the list of file names. So that's called globing, actually, for stupid historical reasons that go back to the 70s. And the main patterns there, the star is the most common one that you see. And the star just, of course, means 0 or more characters that are anything, right? It's just like a wild card, right? It's just you can use more than 1 star in a line. That's perfectly fine. And it's kind of a style thing here, but I probably would have specified it a little more, like SRX start at BAM. You sort of want to have enough context in your star patterns that when you look at them later, you kind of know what files you were referring to. Star.bam could really be anything. You have to know the full context of what directory you were in or something. But like SRX star.bam at least gives you a little hint of what it was that you were doing. Oh, it's some MCBI SRX sessions. Might be enough to jog your memory. Yeah, anyway, you know, these are things that you kind of appreciate more as you go on, just sort of like how you name files and just sort of like how specific or unspecific you can make patterns or stuff. Some of it's all about like kind of like, you know, a lot of times when you're doing scientific work, you're going to be doing the work for a while, and then months are going to go by or years are going to go by, and then you're going to write the paper. Then you got to figure out what you did, right? Because then you got to write the method section and so on. And so sort of like, you'll notice that my file names here are kind of long, but this is so that I can go back years later and look at these and kind of know exactly what I did. This tells me exactly what NCBI session is being mapped here. This tells me that I did some trimming of the reads and kept only nucleotides 11 to 74. Like the beginning of the reads were probably not so good quality or something. So here there was some cycle trimming of cutting the reads down. The aligner was BS Bolt. I chose not to give the full parameter details to the aligner. The genome that I aligned to is GRC Human 38 from Ensemble version 108. That identifies the genome that I was aligning to and so on. Anyway, there's enough details here that I can have a chance of sort of figuring out what I did. I wouldn't just call this sample a.bam or something, right? That's asking for trouble, like when you come back later. And especially when you run analyses multiple times and you know things vary, you know, maybe I tried different aligners or different reference genomes. With your file names having all the details encoded, you can have multiple versions living all in the same directory. Maybe you know, it's very common to do multiple analyses. And then if you're the bioinformatics guy, you'll hand them over to like some of your collaborators or something. And then, you know, maybe they're the ones that, you know, are kind of downstream in the paper or whatever. And then they'll come back to you in a year or two and say, oh yeah, we need the method section now. And you're like, well, which files did you use? Because it's like, I made all a ton of versions of this and like, I sent them over to you. I sent like 10 versions to you. And which one did you use? And they're like, I don't know, but I use this file, right? And at least if you have the file name with all the details inside, you can say, you can recover what you did. Because they should at least be able to tell you which file they end up using. If they don't know that themselves, then what can you do? I mean, that's their fault. Then you keep track of what they do. But you know, anyway, that's the motivation between kind of long file names and you know, in your code and stuff. You know, try to make your patterns not completely wild. Just put a little context in there so you kind of can look at the code later and kind of know with a little more confidence what files it was looking at. Some of the other characters, there's the question mark. I don't know, do you have any ways that we can use that in here? Well, I could maybe use that for these. So these are some logs from the Hoffman Q system, and you can see they're all the same except for this last digit. I'd probably, like if I wanted to look at all of those, I could probably just do a star there and that would be fine. If for some reason the single digit was important, you can use a question mark. A question mark matches exactly one character, whereas star matches 0 to 1, 2, 3, 4, 5, anything. In this case, it'll be question mark and star would be the same for those two. But that's basically the only patterns that you end up commonly using. There are more than that. Another kind of shell pattern, that shell feature expansion that is kind of cool and very useful is the brace expansion. So that's shown here. And that, so the star expansion has to match existing file names, right? It's totally, its job is to match files that already exist. Brace is more flexible. The things it does doesn't have to exist yet. So let me just show you sort of an artificial way first. If you do braces and then commas, it just does all possible combinations in the same order that they're listed. So that's ABE, ACE, and ADE as 3 separate words, right? So that's what brace expansion does. The cool thing, and then brace expansion is like super flexible and stuff. So like, I mean, you can put more or less of them in there. You can nest them. which is kind of interesting. So that does ABE, ACE, then AD1E, AD2E. Now we're back out of the nesting. Then AEE, AFE, and AG. Okay. You can if you put a comma with nothing in between, that's like an empty string. So like that's ABE. The middle thing is an empty string, so that's just AE, and then ACE. That's most of that. And then I think also kind of what's cool is then it's got all the ones with digits. So like if you do 5.20, it expands those into all the integers in between. That's actually a pretty helpful form, because oftentimes you've got files named by sample numbers or something. And even cooler than that is that it actually understands leading zeros as well. So like if you do A005 to 020, it knows that you want them all to be 3 digits. And so then it does 005, 006, 007, and so on. And you can also add another ... and step by things other than 1. So like if you did by stepping by 2, now you'll see it only does the odd numbers, right? Because we started with 5, which is odd, and then step by 2. So it's now 5, 7, 9, 11, 13. Anyway, brace expansion is pretty cool. So like here, if I, for some reason, only wanted to do the grep on the 406 and 407 files, I could do something like grep mapability SRX, and then, 043, 406, 043, 407. That's like the full ID, but actually the 04340 is common. So then I could do like 67 star dot standard out or whatever. Now I'm just searching those two. Anyway, you can combine these however you like, but this isn't the greatest application of brace, but brace is often a pretty cool feature. And I think we did briefly see earlier the history business, where if you type history, you see all of your commands for quite a while. The shell records that in a file in your home directory. If you look at your home directory with ls tilde or cd and then ls, same thing, you don't see everything. That's what the A that I always included. So ls-l gives you this format of listing, but I always do the ls-la. And what does the A do? Well, the A doesn't hide files. By default, ls hides some files, which I always think is a bad idea to hide files. So you'll see the difference. If I'm in my home directory and I do ls, you see some stuff. But if I do ls-a, you see more stuff. In particular, all the files that start with a dot showed up, and there's quite a few of them. Those are called dot files. So by default, ls hides all files that start with a dot, and the A doesn't do that. That's almost always why I always do LA, because I really don't like the idea of hidden files. But one of the files that you'll see in your home directory is bash.bash_history. That is the file that bash is keeping your command history in. If we look inside that file with less, we'll see these are all the commands that kind of it's been logging. The history command in bash just shows that, but also puts the number on the front, so that actually that's how you can pull commands back out of the history. So if I want to see, like, show me all my QRSH commands or something, or show me all my, I don't really have any in this history, or all my CD commands. All right, so like maybe this is a command I want to run again, 1002. Well, of course, in my GUI, I can copy and paste this easily enough, but I could also just pull it out of my shell history. That's the exclamation point character. So if I say exclamation point 1002, that reruns command 1002, and that's that CD command. And so now I've changed directly there. The way that works is it's simply another form of expansion. So if I echo bang 1002, you just see that it just expands into the CD command. And that exclamation point just expands into the CD command. That's sometimes useful. How long your history is, there's a shell variable that controls that. It's probably set in your startup scripts. We haven't talked about startup scripts, but if you kind of say the set command, that dumps all the shell variables. You'll see you actually probably have a ton of shell variables set, some way more and some with way longer things than you might expect. But I think if you grep for hist case, the I means case insensitive. So this is going to show us all the shell variables with hist in them, either in their value or in their name. I think the one that matters is this hist file size. So you can see for me, it's set to 1,000. So it's keeping my last 1,000 commands. All right, let's talk about regular expressions. Here we use grep in the most simple way possible. We were just grep mappability. That actually is a pattern, but it's just a literal string. There's no fancy pattern in there. That's an easy one. But of course, grep, I think you saw in workshop 1A a little bit about regular expressions and all the fanciness of that, of what you can do. So here's, let's go through some of the regular expression power. So here's an interesting file to use. In user shared dict words is a very long file containing like all the unique words there are, like whatever. It's like a big dictionary, but it's got a lot of words in it. Okay, so like we can less it, and I'm just going to hold down the space key, and you can see it's just like full of words, like in dictionary order. In fact, how long is it? We can use the WC command. It's almost 500,000 lines. It's got a lot of words. But I'll use this file just kind of as a nice example of grep, because we can now grep out for certain words with certain patterns. Okay. So the pattern you almost always want to use grep with is the -e, and then the pattern goes here, and then the files that you want to search go here. And if you don't give any files, grep will search standard input. Grep will dump its outputs to standard output. So the first -E means your pattern is what's called an extended regect. Extended regular expression. That's sort of the most powerful form that grep does, and you might as well always just use that one and not have to worry about like all the flavors of regular expressions grep does. Just always use the E flavor, and then the little e introduces the pattern. Sometimes you can get away without it, but like suppose the pattern starts with a dash or something, it would be confused with an option, and so the safest thing is just to tell grep that the dash little e means the argument after this little e is the pattern. Okay, so the way I recommend using grep is to always use this E, a little e, and then as the third argument goes your pattern. Now either put the files you want to search, or you're using this in a pipeline, and you're going to search standard input either way. But we're going to search the file user shared dict words, and we're just going to plug in different patterns here. The patterns often contain funny characters that the shell wants to play with. We already know that the shell responds to things like $signs and parentheses and curly braces. All kinds of characters are special to the shell and activate special shell features. Well, the regular expressions often also use the same characters. And in that case, we don't want the shell to play with those characters. We want the characters to go unmolested to grep, because grep is going to interpret them according to regular expression language. And so that's why single quotes are almost always the thing that you want to put the pattern in, because the single quotes disable pretty much all the shell stuff. Anything we put in here now will pass literally to grep. And so all the weird regex characters that also happen to be shell funny characters make it to grep without the shell molesting it. So, okay, so now we can play here. So we could grep for something like this, which is a pattern that doesn't have any special characters in it and all, and that just is a substring match, like we've already seen, like we did with mappability. This will find all the words with THERE there as a contiguous substring. The default for grep is a case-sensitive match. So if there's any capital T's, H's, E's, or R's, those aren't going to match. We're looking for lowercase THERE anywhere in the line. And so you're going to see a whole ton of words that come out. All that could be at the beginning, could be in the middle, could be at the end. Okay, there's quite a few. It's not that many, but there's there's a lot of words with there somewhere in them. There itself by itself should be there too. So there it is. There's there by itself. Okay, here's slightly fancier pattern. We could ask for all the words that end in ER or ME. Okay, so the $sign only matches the end of a line. The parentheses form a group, and the pipe symbol now means or. It's the thing on the left of the pipe or the thing on the right. So we're looking for words that have an ER or an ME in them, but after the ER or ME, we have to be at the end of a line. In other words, words that end in ER or ME. So there we go. Now we're getting words that end in ER or ME. Okay. How about this one here? So, and there's this one. Okay. The caret sign, this is Shift-6 on my keyboard. That's a caret. That means only match at the beginning of a line. I already said the $sign only matches at the end of a line. And that means the stuff between the caret and the $sign has to match the whole line, right? So the default is substring match. But with the caret and dollar sign there, now you're asking the line, the whole line has to match this exactly. Then we have this bracket A to Z and bracket 0 to 9 and a star. The brackets mean any character, any single character inside the bracket. So since this is at the beginning of a line, this means has to start with a capital letter, right? Then you've got this. Well, this means digit. Has to be 0 to 9. But we got the star here. What does the star mean? The star means repeat the previous thing 0 or more times. So it's a whole line. It has to start with an uppercase letter and then be followed by any number of digits. So you see, starts with a capital letter, happens to have 0 digits after it. That's okay. Starts with a capital letter, happens to have 1 digit. That's okay. B911 starts with a capital letter, has only digits after that. All okay. So what you see here, that's exactly that. Okay. All right, what's the next one? So it's this one. Okay. So again, I've got the caret and the dollar sign, so we're finding matches to the whole line. The first letter has to be a capital, a lowercase s. But then there's this bracket thing and a plus. We already know the bracket thing is any of the letters inside. So this has to be a single A, E, R, or L. But what's the plus sign do? The plus sign is like star, but it doesn't allow 0 matches. It has to be at least once. So it's a word, starts with little s, and then only contains A, E, R, Ls, at least one. So it's words of a length at least 2, start with little s, and are composed after the s of only A, E, Rs, and Ls. Things like seller, right? Here's seller, right? Beginning of line, little s, then contains 1 or more characters, but all the characters have to be A's, E's, R's, or L's. And this one is E's and L's and R's. Okay. How about like this? We got the caret and the dollar sign again. So we're doing whole lines again. This M at the end means has to end in little m, but we now got this funny stuff at the front. We've got a period and then curly braces 4, 5. The period matches anything, any single character. The curly braces are kind of like star and plus. They control number of repetitions. Star is 0 or more repetitions. Plus is 1 or more repetitions. Curly braces are, you tell me how many repetitions. The 4 and 5 mean 4 to 5 repetitions. If I said 0, comma, that's the same thing as star, 0 or more repetitions. If I said 1, comma, that's plus, 1 or more repetitions. If I said 9, 11, that would be 9 to 11 repetitions. But what did I have? 4 or 5. So it's words of length 5 or 6 because it's 4 or 5, but we put a little m on the end. So the part on the front is 4 or 5 letters long, which put the little m on the end is 5 or 6 letters long. So it's words that are 5 or 6 letters long, end in a little m. Here's another one. It's okay. The caret, we don't have a dollar sign anymore, so we're not worried about matching to the end. We do have a caret on front, so we're looking at the beginning of a line. Then we have an A, must start with a little a. But then we have in parentheses 3 dots. Well, that's 3 characters, any 3 characters. But then there's a \1. What does that mean? Well, when you have parentheses, that's called a group, and the groups get numbered in the order they appear in 1, 2, 3, 4, 5. So this parentheses 3 characters is group 1. \1 means the same thing as group 1. So what this is words that start with little a are at least 6 letters long, but the second, third, and fourth letter as a 3-character string are the same as the 5th, 6th, and 7th character. In other words, they have to double, right? So it's like little a, then 3 things, then those 3 things again. Like, so it's got to be like some kind of double, right? You know, it's like a, well, we'll see what words match. Let's see what words match. Not many match. One of them is alfalfa, okay? Because it starts with little a, but then you've got LFA, LFA, right? Now, we didn't require to be at the end of the line. That one happens to end of the end of the line, but like alfalfas, okay, that's maybe a little better example because it starts with little a, then has 3 characters, which are then repeated, and then we don't care anymore because that was the end of our pattern, right? So then it's free after that. So the S is okay. Not many words like that. Assessed, assessancy, that's hard to say. Anyway, you start to appreciate you can do some pretty fancy things with these. And you know, when you kind of got DNA strings and stuff, some of these are actually pretty useful. Let's see, what was the next one I had? I mean, we're about out of time here. We'll just okay. Why don't we do the crossword one? Actually, that's kind of the next one, right? So actually, if you're a fan of crosswords, this user shared dict words thing is a big boon for you because, like, you know, you're at a situation where you're like, you know, it's like a 10-letter word, and then you know you got like some of the cross numbers, right? So it's like, oh, it's like blank n, blank n, blank w, blank 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 e. What word is it? Well, now you just do your grep, right? So we'll just grep user share dict words. What pattern should we use? Okay, well, we're not going to want a substring match because we know it's got to be like exactly 10 letters. So start of line, end of line. Okay, then it's any character. You see the pattern here where this is the partial pattern we know from the crossword. Any character and then an N. I'll type it exactly in there and then I'll show you the little problem with this. And then any character and an N, and then any character and a W, and then 3 things we don't know, and then an E. Okay, but that's not going to match anything. Why is that? Well, because I typed them in uppercase and most of this file is in lowercase. So I could change these to lowercase. The word is actually unknowable. It's actually unique at that point. Or I could have told grep to be case insensitive. So I could have put a -I here. And that tells grep every letter doesn't matter uppercase or lowercase. So that would also work with -I. Grep, if you haven't done it yet, grep --help will show you some of the options for grep. You could have done man grep. And you'll see here that, like, for example, -I, ignore case distinctions in the pattern and the inputs. V inverts the match. So if you do -V, you're getting the lines that don't match the pattern rather than the lines that do match the pattern. Right? So there's all kinds of stuff in there. Like I think -N is a line number. No. Oh, because do I have the -I again? Yeah, okay. So this tells me that the matches are on line 444,843rd and 440,844th lines of the input file are where the matches are. That's the -N as the line number. Remember, the -I is for the case insensitive. The E enables the extended regeps. Little e says the next thing's the pattern, and so on. Anyway. Yeah, anyway, that's good for today. So all right, so yeah, so our big project tomorrow. This kind of hopefully got your juices flowing, you know, kind of brought back stuff you learned, but, you know, we're getting into more details now. Tomorrow, our big thing is to kind of work on building up those bigger, meatier pipelines that do real work. Okay, so I'll stop the recording.